Okay, and here we are. So how are you doing tonight, Amos?
Pretty well. A little bit tired myself. It's a long day, but whoops, that's not what I wanted to do. Yeah, but yeah, all in all,
Yeah, don't
in
post
the
the
positive.
link.
Do wait.
Start getting all kinds of people connected to you. Probably not though, given that I don't think there's anybody actually watching. But
Yeah, how about you?
doing all right. A little tired myself, you know, but had a pretty good quiet Christmas, so I should be well rested. But I actually been doing quite a bit of work with Raph and Brian lately.
Nice.
We're sort of working on a new feature for retools that we're kind of excited about, and then also just a lot of stuff with I think I've told you about this thing we're working on called the ephemeral tools. So
Yeah,
yeah, just a lot going on with that stuff. So
that's
so that's
awesome.
been good.
Yeah, I'll have to catch up on that. It's for too long.
Yeah, yeah.
Yeah.
Um, so I'm wondering if you can open up the file that we were working on last time, if you recall how to navigate to it.
Yeah, I gotten it open.
Ah, there you go.
And that's what I had actually meant to copy over because I was trying to. I hadn't had time to do anything um, before this week, with the
Sure.
holiday and travel and
Sure,
everything.
been
So
busy, so you did not
I
get a
was
chance to look it back over, which is fine.
nah,
Which is
about
fine.
10 minutes. 10 minutes ago, I did. I'm like, now wait a second. Yeah,
So we can just maybe briefly recap some of this. I do think it is probably a good idea if you kind of go over stuff a little bit, at least in the middle of the week, just because otherwise we're going to wind up recapping the same things a great deal. Because
right,
a week is long enough to forget a lot. But
totally.
but
I'm less
yeah,
forgetting than I was last week. That is definitely true. But I know that last week was pretty much more or less a repeat of the week before. I mean, I know we made a little bit of additional headway,
to
but
some degree, it was also last week was a little shorter than usual
yeah,
as well. So but yeah, let's just kind of, go back over some things. I think, I don't know if you want to either copy everything you have there into the top pane of the other one, or I'm not quite sure. I think if you hit run right now, you may it will probably give you a REPL below this. Right now, this only has sort of a text buffer. It does not have a REPL. You see what I
yeah,
mean? So you
yeah.
kind of want something I think where you have this stuff both at the top and you also have a REPL to type into, regardless of how you achieve that, which could be just copying stuff over to the other window
Will it
or
do it like this?
okay, yeah.
It's,
And just to satisfy my very very picky sense of formatting, if you could put a line between the sharp line racket and that first define, it doesn't make any actual difference. I'm just fairly I don't know. I'm sensitive to white space. I don't like things being sort of tacked together that are not logically related.
mm-hmm.
So yeah, let's take a look at let's talk briefly about the stuff we've talked about before, right? So
Yeah,
we talked about entering things at the REPL and having them evaluate, right? And then the REPL prints you out what they evaluate to.
and loops
And
back waiting.
and one of the things that's pretty important about that is that there's a set of rules for how things get evaluated. And that set of rules basically always holds. Although there's one exception we haven't really talked about yet, but that we have seen. And I kind of do want to talk about that briefly in a minute. But so, the rule if you put a number in, if you put in a number like 6, right? What's the rule for how that gets evaluated?
To itself.
Right.
I mean, it's yeah, it's
Numbers
its own.
just evaluate to themselves.
Yeah,
But what if you type in something like pi?
that has its already evaluated value within the
Right. So what is
within.
pi when you type pi in? What kind of a thing is it?
It's not a function.
It's not. It's a symbol.
Symbol.
It's a
Yes,
symbol.
thank you.
So pi is the symbol, and we talked about the use mention distinction. Do you recall that?
Yeah, like basically, um, it being put in use and it being referred to, the difference between those two. Not very well said, but
Right. Pi itself is a symbol, but it's bound in this case to a number, which is 3.14159. So we can talk about sort of the symbol pi itself, or we can talk about pi in terms of what the value that pi is bound to is. And it's good to not confuse the symbol for what the symbol's bound to, because those are actually two different things. And do you remember how to so when you type the symbol in, so this is a rule, right? When you type a symbol just straight into the REPL, that symbol evaluates to whatever that symbol is bound to within the current environment that you're in, right?
mm-hmm.
But what about the symbol itself? How can you get the REPL to give you back the symbol?
Quotes, I think.
Quote, that's right.
Quote, yeah.
So quote is actually a special form. So what you can do is type an open paren quote, that is to say, spell out the word quote, and then pi, and then close the paren, right? Paren, not double quote. Yeah, try that out. But you can also type, you see that when it printed it out to you, what it actually printed it out to you was like a single quote pi. So if you type in single quote pi, that also, that is a shorthand for the thing with the open paren quote pi, right?
Okay.
So what quote does is it stops evaluation of things, basically, right?
It stops evaluation.
Sure, if you evaluate pi, what do you get?
Right. Okay.
You
Yeah.
get what it's bound to.
Just feeds it back, feeds the symbol back to you.
It feeds the symbol back to you, and you can quote things that aren't symbols too. But when you quote
Yeah.
something, it just sort of stops evaluation dead. And we're going to see lists here. We're coming right up on seeing lists here. And so, for instance, you can quote a list as well. Because we've kind of seen lists already in a weird kind of way. Let's talk about. So we talked about functions, for instance, things that can be applied to arguments. Procedures are one thing that can be applied to arguments. There are other things, and we've seen some of them. But certainly procedures, like for instance, the square that we defined above as a procedure. So what is the rule? How do you apply a procedure to arguments?
Well, you use parentheses to define the procedure, and then a separate set of parentheses to
Right.
to enact that procedure with symbols or values.
Well, there's a very specific rule that we talked about, and
Okay.
it has to do with open parens. When you see an open paren, the
Hmm.
thing that comes directly after the open paren is supposed to be something that is going to evaluate to a procedure.
Okay. Right.
And so it'll evaluate that thing to a procedure, and then it will apply it to anything else within the parens before the closed parens, right? So if there's one thing before the closed paren, it will apply the procedure to that single argument, right? If there's three
Hmm.
things, it'll apply the procedure to all three of them. If there's nothing, then it will call the procedure, but with no arguments at all, right?
Hmm. Okay.
So how would you can see, have you hit run yet, by the way? Have you
No.
evaluated what's in the top? You should probably evaluate what's in the top because we do have some stuff up there. So for instance, we've defined square, right? Square is a procedure that we made with lambda. So how would you apply square to 6?
Then just be.
Yep, there you go. And plus is a procedure too that we've seen, addition, right? Which is bound to the symbol plus.
Mhm. Right.
So if you wanted to add 3 and 4, how would you go about doing that? Right. And so you can see this rule in action here, which is that when you see an open paren, the very next thing is something that has to apply to, the very next thing is something that has to evaluate to something that can be applied to arguments, typically a procedure, right?
Okay.
And so that's just a rule. What happens if you put pi, for instance, in parentheses? Right. And you can see the error is telling you exactly what went wrong here, right? Pi is not a procedure. So if you see an open paren and you see something after the open paren, that thing is expected to be a procedure. Now, there are some exceptions to this, and there's some that we've already seen, right? Like take a look at, do you see what we've defined square to be? Which is
The
that
lambda.
lambda of x. So note that
Yep.
that's something that evaluates to a procedure, right? You can actually use an open paren and then put that lambda expression after it and then apply it to 6, close up your parens. Why don't you try doing that right now? Well, okay. But hold on. Let's think about this for a second. Okay. So the rule is that expression up above, that lambda, including its open parenthesis, right? That's something that evaluates to a procedure, okay? If we want to apply it to 6, we're going to have to put that entire thing after a parenthesis. Do you see what I'm saying?
Uh,
Including its
oh,
own open parenthesis, right? So we're going to start with 2 parens, not 1, if we do
okay.
that, right? This is why, and we were talking about this before, being very, very literal about these rules is important, right? The thing that
Well,
evaluates to a procedure here is this lambda form, which includes its own open paren, right? So if we want
yeah.
to apply that, we need another open parenthesis. Do you see what I'm saying there?
I do. I think I do. The thing that is like, so square is being defined here, and lambda is square is being defined as a specific procedure. I guess I'm like, and then when you hit run, now square is defined as that
Right.
procedure inside the lambda,
So
and
let's
the
actually back up a little bit here for a second. Why don't you take off that first paren and just put in the lambda expression? Because this is really, really important, right? Well, no, not lambda 6. What is lambda?
I'm not sure. I'm still unclear on like the difference between lambda and define, really.
So define just binds a value to a symbol. It can do a little bit more than that. And there's a special form for it that we talked about that actually creates a procedure and binds it to a name. But the typical use of define is just to bind a name to a value. So you can see that very first line there. It's define pig 42. And what
Yeah.
that does, if before doing that you typed pig in, like you can try typing in pit, for instance, PIT right now.
Yeah.
Right, just give it a
Yeah.
try. It's not bound to anything. So that's an error, right? Because the rule for evaluating a symbol, if you just type it at the REPL, is to say, okay, what is this symbol bound to in this environment? And if it's not bound to anything, it's an error to try to evaluate it.
Yeah.
Note that you can still type in quote PIT, though. Try that out. Single quote.
Oh.
Yeah, you can also type that in double quotes. You'll get the string pit, but the string pit is not the same thing as the symbol pit.
What's the string bit?
A string is a representation of text. So this is the text pit. But the text pit is not the same thing as the symbol pit
Okay.
with that name. And so we won't worry too much about strings right now. They turn out to be very, very important in programming. There are some types of programming where you deal with strings a great deal, but we're not going to worry too much about strings right now for a little while. But symbols we care a great deal about right now, partially because we bind symbols to things. That's a huge part of what we've been talking actually about is how names get bound to values. And when we say that a name is getting bound to a value, it's really a symbol being bound to a value. So lambda is what creates procedures.
Yeah. Okay. Yeah.
Okay. And it's got a very specific syntax to it, which is sort of what I want to talk about in a minute. But you can't just say lambda 6. That's not the syntax for lambda. Lambda has a very specific syntax of its own, and you can see that syntax up there. If you take that entire lambda expression, like forget about the define and the square, just take that
Yeah.
lambda expression and copy that into the REPL.
Well, just the single paren.
Yeah, exactly. Just that form. And you have to like did you get the ending paren as well? Yeah. Well, it's got 2 ending parens, actually, right?
Well, that's the boom, boom. Oh, yeah, I see what you mean.
Yeah. There you go. Okay. And if you put that in, you get back a procedure. That's what lambda basically does, is it makes procedures. And it's got this is, what we've been talking about. It's got this very specific syntax. There are three parts to the lambda. And first is just the symbol lambda, right? That says, okay, this is lambda, where, it identifies what you're doing. The second part of it is an argument list. And that's just in parens the arguments that this procedure is going to take. In this case, it takes one argument. If we were writing a procedure that took two arguments, like x and y, and you can see we've done something. We'll talk about the defined syntax again in a second here up there, which is kind of a shortcut. But you can see it's got the argument list. So the argument list is, okay, this takes one argument. And that argument, we want to bind that argument to the name x. We could have picked any symbol here, right?
Yeah.
We picked x because x is, pretty common for this kind of thing where it represents an unknown number.
And it could be multiple characters. Yeah.
It could be multiple characters. Yeah.
So in this one here with the head to 7 and 8, it's got two arguments, x and y, because there's the space in between.
That's right. That is an argument list. Yes, that's an argument list of two arguments, because what we're making is a procedure that takes two arguments. And in fact, this is just a procedure that adds two numbers together. It's a pretty useless procedure because plus already does this, right?
Yeah.
Right. But we were using this to sort of show how you could use a lambda in place of a let, for instance. That's why we defined that one. But it's a useful example. So that's the second part of a lambda, is that argument list that says, okay, this is how many arguments it takes, and these are the names to bind those arguments to when executing the body of the lambda. And then the last thing in the lambda is the body of the lambda itself. And so the rule, when you actually apply the lambda to the arguments, what happens is that it is as if the body of the lambda were evaluated with those symbols bound to the arguments that are passed in. So when you call square 6, right, as you did above, what happens is it basically takes the body of the lambda that we've bound square to, right? We bound square to a lambda. So first, square gets evaluated. And it says, okay, square is this lambda. Or the result of this lambda, actually. It's this procedure that the lambda defined. And so the rule for evaluating that procedure is you take the body of the lambda and you evaluate it
against R
with the arguments from the argument list bound. With the argument that you passed in is bound to the symbols in the argument list. So in this case, it's got a single argument, which is x. You passed it 6. Within the body of the lambda, x becomes bound to 6, and then you evaluate that body, right? So you go times x is 6 in this case, right?
So I think it's starting to kind of come together a little bit. So if the lambda procedure is defined as square, and then you tell the computer to take square and evaluate, I don't know if my language is right, argument of 6 is always going to, whatever you ask it comes after square is going to kind of stand in for the argument of the procedure of that's represented by square. I don't know if my question made sense there.
Kind of. Yeah, I think I see what you're getting at. So first of all, what we say about these procedures is that they are applied to arguments. So that's a very important piece of terminology. You apply a procedure to arguments. So we apply the procedure that square is bound to. So note that square is not at square, and this is where we get into this use-mention distinction, and this is why I really wanted to make such an important point of it, is that you have to bear this in mind. So square, we can use the word square to mean two things. Square is a symbol, right? Square is a symbol with like 5 letters in the symbol's name, SQUARE, right? That's one thing of square. But we can also say, it's very common to say, and that's the mention part of the use-mention distinction. We're mentioning the symbol square. But it's also very, very common to say square is a procedure that squares an argument. squares its argument, right? You apply it to an argument and it squares it. So when we say those two different things, note that we're really using square in two different ways there,
Yeah.
right? One is
Yeah.
we're actually talking about the symbol square, and the other is we're talking about the value that square is bound to. And so there's nothing special about the name square, right?
Yeah.
We just chose that name because it's a pretty accurate description of what that procedure is
Yeah.
doing. We could have bound Fred Flintstone, the symbol Fred
Yeah.
Flintstone, to that procedure, and it would still square numbers, right?
Wow. Yeah, but we'd have to do it all one word.
Well, you could put a minus sign in there. You could type
Yeah.
Fred minus sign Flintstone as well, right?
Yeah.
That's a perfectly valid symbol in Scheme. So the fact that the symbol is square has nothing really to do with this. We just named it square because that's a good name for it because it is what it does.
Yeah.
Right? But there's nothing special about that. It's not squaring numbers because we bound it to the name square.
Yeah.
It's
Yeah.
squaring numbers because we defined a procedure that squares numbers.
And the lambda.
And that's what the lambda is doing, is defining
Yeah.
that procedure. And the lambda has that set of rules that I was talking about, right? It's got three parts. It's got lambda, which kind of tells you what you're doing. It's got the argument list, which tells you how many arguments you're getting and what symbols to bind them to. And then it's got the body of the actual procedure. And when you evaluate the procedure, what happens is that body gets evaluated. When you apply the procedure to an argument, let me be precise about this.
Yeah, and the argument, when you say square 6, the argument is 6.
The argument is 6, yes.
Okay.
And so what we do is we evaluate the body when you apply the procedure created by that lambda. When you apply that procedure to the argument 6, we evaluate its body, which is that like times XX in there. That's its body. We just evaluate the body, but what we do is we bind X to the procedure, right? We say, okay, X is 6 now, because that's what you applied it to, right? And if you said square 8, you'd do the same thing. You'd evaluate that body, but X would be bound to 8, and you'd get 64. So does that all kind of make sense?
Yeah.
Okay.
Yep.
So then to define square lambda, that's just so we have a way of referring to it later. We need some way, and we don't have to do that, right? So let's go back to what we were doing before, which is, so you just evaluated that lambda, and you see that you get a procedure back, right? How would you apply that procedure to an argument, though? Because there's a rule for this, right? Remember the rule for applying procedures to arguments.
The procedure has to come right after the open parens.
That's right. So why don't you try doing that? Using a lambda, using the lambda you used on the line above, why don't you apply that to an argument?
Same procedure.
Yep, just do the same thing and apply it to 6. Well, you do need, you need to give it an argument.
Okay, yeah.
And you've got one more paren to close up.
Yeah.
Yeah. And actually, there's a problem with your parens. So, yeah, there is a problem with your parens.
Oh, the 6 is in with the lambda.
Is it right? Is inside the lambda.
I got it. Right. Lambda needs to be independent. There we go.
Right. And so you see how applying these rules in a really literal way just sort of makes everything work out, right? That lambda evaluates to a procedure. And we know that if you put if you have an open paren and then you have something that evaluates to a procedure, then you apply that procedure to the rest of the arguments that are inside these parens, right?
Yep.
Okay.
So if I'm just trying to think here. I guess this is a procedure that can only take one argument, so it's not like I could have
Right. Try passing it 2 arguments.
Yeah, that won't make any sense. I was gonna see what we could do. What happened?
Okay, you have 1 extra paren there.
I know this because I was gonna put it. Well, I guess it doesn't need a paren for the argument. The argument is can
Right. You
share
don't need an extra paren to pass more arguments. You just put one more
right in
argument
the
in there.
space. Yeah. Yeah, it's not. I mean, I could just know that, like, how's it supposed to figure out which one, what you're.
Yeah, so it tells you arity mismatch. And what arity means is how many arguments the procedure takes,
Mhm.
essentially, right?
Yeah,
So it's an arity mismatch.
tells you specifically what the problem is. That's
It
nice.
tells you specifically what the problem is. And depending on your
Yeah.
programming language and exactly what the error is, error messages range from very informative to extremely hard to interpret.
Mm.
So you get better at interpreting them. And it's definitely an important skill because I'm going to say if you're anything like me, you'll probably have a lot of errors while you're writing code. Not everybody does. I mean, Don Knuth is a very famous computer scientist who wrote a something called Tech, which was really one of the first sort of computer typesetting languages. And he wrote this whole system with this language to be able to do computer typesetting. And the story about this is that he mostly actually wrote it on paper and then gave it to an assistant of his to actually enter into the computer. And that it apparently pretty much ran. So that's impressive. That's not how most people program these days.
Yeah.
You used to have to be better at that kind of thing, right? Like in the days of punch cards, you'd basically make a whole bunch of punch cards and then you'd bring them to a lab. You didn't even have access to the machine that they got fed into, but you'd put your program in literally by punching holes in these paper cards. And you'd bring them this big deck, possibly of hundreds or thousands of cards, and they'd feed the punch cards into the machine and they would try to run your program. And you'd come back the next day and get the results. Well, if there was an error in your program, you'd come back the next day. They'd be like, "Oh, here was your error," and you'd have to sit down and figure out what had happened with the punch cards and like fix it. So I think people who grew up programming in that kind of an environment got used to being very, very careful about things.
Yeah. Yeah.
But it's a bit of a luxury to not have to be careful, right? You can go very, very quickly and sort of not worry too much. You know, if you make a
Yep.
mistake, hopefully the computer will catch it. You do have to be careful about some things, though, because certain types of errors, like this, for instance, the computer's good at catching. There are certain types of logic errors that the computer is bad at catching. And so you don't really want to write bugs into programs that actually are deployed live. And we
Mm.
can talk more sometime about like how you do your best to avoid that. Unfortunately, we kind of all, at least every once in a while, release bugs, right? It's the amount of work that it would take to never release a bug would probably not justify itself.
Right. Yeah. Well, I have a question here on the previous one where I misplaced my prints. Um, it seems like I would have had an error. I was just curious to actually run this because
Actually,
it's
no. Uh, you wouldn't have. So try taking that. We kind of touched on this a little bit. Try taking that, put it in there, and give it an argument so that you don't have an arity mismatch. Just apply that to anything. It won't actually change. Don't apply it to 6, though. Apply it to 12 if you want. No, leave the 6 where it is, right? That's
yeah.
part of the lambda, but just apply that entire lambda to, say, 12. I have a reason for not wanting you to apply it to 6.
Oops.
Yeah, yeah. Scheme, right. Scheme, racket requires that you be at the
I
end of
gotta
the line.
yeah.
So that lambda expression is a procedure that will always evaluate to 6.
You know,
And
for its
we touched on this a little bit before, and I
yeah.
didn't, which is that you can actually have more than one expression within the lambda. The body doesn't have to be a single expression. It can be a series of expressions. And those expressions will be evaluated one after another when you evaluate, when you apply the procedure.
Okay.
But
And
only
this
the
is
value of the last one will be returned. The values that all of the
great.
other ones get. So there's no point in doing it unless the other ones cause side effects. If you were to put in instead, so if you take that lambda and so put it down on this next line again, but don't hit return. And inside that set of parens that's the times XX, instead say print line, right? PRINTLN. And so here is a good example of where you want to use a string, right? So hit space because you want to print something out. You want to print out a string.
Mhm.
Now it double quotes, returning 6. And now go to the end of the line, right? So you don't wind up, so you can actually hit return. Yep. Oh, you do have to apply it to something again, right? So apply it to 12 again. And you can see that in this case, it actually kind of makes sense to have these two expressions there. I mean, this is a pretty nonsensical procedure, to be perfectly honest with you. It's constant, so it just always returns 6, but it tells you that it's doing it. So you probably wouldn't really write this procedure, but it's an okay example. And here you can see that there's sort of a point to having two expressions there, because the first one is actually doing something to the outside world. It's the value that expression evaluates to is getting thrown away. But we don't care about that because we don't care about what that evaluates to. We care about what it does, which is print something.
Mm-hmm. So this just not argument. This procedure, the print line procedure,
Yep.
is in parentheses, and the 6 is not, because the 6 is just a single character.
The 6 is just, again, each of these things is just something that evaluates to something. It's a form. And that's kind of what a form is something that will evaluate to something without throwing any errors, right? That's what we mean by it when I say a form. And so 6 is a perfectly valid form. 6 is a number. It evaluates to itself, okay?
Right.
So open parens times x, close parens, is a perfectly valid form, at least as long as x is bound to something. That's a perfectly valid form. It multiplies whatever x is bound to by whatever x is bound to, right?
But it needs its parentheses to separate it from any other.
It needs its parentheses because that's the rule for applying procedures, right? So that form is a form that applies times to two arguments, right? So it needs that paren. This is what I was talking about the rule with the parens. The paren, if you want to apply the times, the multiplication procedure to things, you use parens for that. That's what parens do.
Right, because it's got a procedure within it. The 6 is not a procedure.
The 6 is not a procedure, it's just a number.
Yeah.
Whereas the sort of open paren times x, close parens, that's not a procedure, but what it is it's a form that applies a procedure to arguments, right?
Okay.
And that's what we want to do when we write square, is we want to apply multiplication to whatever the argument you passed in is. That's how we square things, right? Yep. So that's why the parens are there, is so that you can apply that multiplication to things. But yes, the body of a procedure does not have to involve parens. It typically does. Almost all procedures are going to start off by applying something that can be applied to arguments. They almost all do, because otherwise they're probably going to wind up being constant, right? Mm-hmm. Like this one is. And most of the time you don't write constant functions, in Scheme at least, right?
Okay.
You don't very often write procedures that always return the same thing, unless, of course, it's a procedure that is only meant to perform side effects, in which case it may return no value at all, right? So it'll be sort of constant in that sense. It doesn't return a value. Because you could write a procedure that was only for printing something, right?
Mm-hmm.
And then, that procedure wouldn't really return anything because print line doesn't return anything.
Yeah.
But we're really more concerned right now with procedures where we care about the return value. And so typically, when you care about the return value, you write procedures that can return more than one value. Because if you write a procedure that can only return one value, you might as well just put the value there most of the time.
Right? Yeah.
So these are kind of the rules for the open paren for applying things. And you'll note here, let's remember, if you look at line 7 up in the top, right, where we have to find square 2.
Yep.
So most of the time, sometimes you really want a procedure that you only want like right now because you want to apply it to something, and you're just not going to ever call it again. You don't need to refer to it later on. And so for that kind of thing, you really will use a lambda sometimes. You just get what's called an anonymous procedure and you immediately apply it, which is what we've been doing with this.
Yeah.
Most of the time, though, when you define a procedure, you're going to want to call it more than once. You're going to want to call it somewhere else, right? That's why you're defining it, is so that you can... And when we say call, that's kind of a synonym for apply it to some arguments, right? I mean, the technical, the really precise way of talking about what we do with procedures is we say that we apply them to arguments. But, we also just sort of, we can say that we call a function, call a procedure. And
Yep.
so we want to bind it to a name. And so you can see that when we define square to be this lambda, that's sort of basically what you're doing, right? You're defining a procedure using lambda, and then you're binding it to a name. But that syntax is a little unwieldy, right? So what you see on line 7 is a shorthand form of that. And it's a special syntax that define has, where you basically, instead of using a lambda keyword,
Yep.
you have a list of things. So normally when you use define to bind a symbol, it's just define and then the symbol and then the value you're binding it to, right? Just like define pig 42 or define square, whatever this lambda expression evaluates to.
Yeah.
But note that this use of square is syntactically slightly different because we've got square 2 and then x in parens here. And when you have define and then you see something that starts with parens, that's signaling to define to do something slightly different than what it normally does, which is to say, okay, the first thing in those parens is a symbol that we're going to bind a procedure to. Then everything else in the paren is an argument to that procedure, right? So this is an argument list, just like in the lambda, except we put the name that we want to bind the function to at the beginning of the argument list.
Okay.
And then we just put the body there, right?
Yeah, I think I didn't understand it last time. That makes sense.
Yeah.
I should do the same thing. 36.
Yeah, exactly. So you didn't apply square 2 to 6 there. You just put two values into the REPL, and it evaluated both of them. So it evaluated square 2, told you that's a procedure name that's bound to square 2, and then it evaluated the 6. How would you actually apply square 2 to 6? Yeah, there you go. And again, this is just a case where we want to be very literal about what the rules are, right?
Yeah.
The rule for evaluating a symbol is just to evaluate it to whatever it's bound to, which in this case is a procedure. And when you put two values at the REPL, it will just evaluate them one after another.
Okay.
And it will print you out what each of them evaluated to. So yeah, to apply it, you just have to put it in the parens. So most of the time, when we define procedures that we want to bind to names, we will use this special syntax of define. It's just, I think it's a good idea to understand under the hood what's really going on is there's this lambda and it's getting bound to a symbol, right?
Yep.
I don't know, SICP does it sort of the other way around, where they introduce, the define syntax first. But I kind of like introducing lambda right off the bat and really showing that interaction with define. So either way, as long as, you kind of get there in terms of understanding both of these things, it's fine. You can see we used that special syntax to define sum of squares as well.
Yep.
You can see how that works, right? It's just, again, you have this argument list, which is xy, but we start the argument list off with the name that we want to bind the procedure to, which is sum of squares. And then we have the body, and the body is add this and this. And note, by the way, that you could also have used square in that body. That times xx and that times yy.
Because we've already defined square.
You've already defined square. They could be square x and square y. This would be exactly the same, actually, because, of course, what square actually does is it has a body that is times xx. Note that the names are independent in this case, right? If you put in square x and then square y as these two things in sum of squares, when you applied square to the y, within the body of the square, that value that was y in sum of squares would be bound to x within square. Do you see that?
I lost you there for a second. What was it? We're still on line 9 here.
We're on line 9. So why don't you do me this favor, actually? I don't think we care about anything that's at the REPL right now. Why don't you actually don't put it in the REPL, but change it so that it calls square instead of doing times xx and times yy.
Up here in the...
In sum of squares. And now hit run. Hit run because you're sort of out of date. You've modified it. So call sum of squares with like 6 and 7, for instance.
Six and 42. Wait, no. Wow. 36 and 42 should be 6 and 2. Oh, no, it's not 42, it's 49.
So
Okay.
it's 36 plus 49. That
Yeah.
looks about right to me. I know it should end in a 5, right?
Yeah. No, it is right. Sorry. I was multiplying 6 and 7 instead of 7 and 7 for the square.
But let's actually think about what happened here in terms of these applications. So you call sum of squares xy. So what it does is it evaluates the body. So, and this is something we should actually mention. Well, okay. It evaluates the body of sum of squares, right? With x bound to 6 and 7 bound to y.
Mm-hmm.
Right? So we're going to do an addition. One thing about scheme is that when you apply a procedure to arguments, those arguments are evaluated right then. That's not the only way it can work, and that's something we can talk about maybe another time, I think. But that is how scheme works, right? Which is that when it sees that plus square x and square y, it wants to add those two things together, and it says, okay, what I'm going to do is simplify those things first. So I'm going to apply square to x, and I'm going to apply square to y, right? Which in this case are bound to 6 and 7.
Yep.
So we go and we say, okay, we're going to evaluate the body of square, which is times xx, with x bound to, and we're passing it x here, which we had bound to 6, right?
Yep.
So note then, though, that we call square y, right?
Mm-hmm.
We evaluate y in this case, which evaluates to 8, to 7, right? That's what you did it. And we pass that into square. Note that when we're actually evaluating the body of square, even though that was bound to x, to y in sum of squares, and x was bound to 6, when we call square y, it's going to bind the value that y is bound to, which is 7, to x while it's evaluating the body of square.
To x? What do you mean?
Well, so square, you can see that the body of square is times xx, right?
Oh, to that x. And
that x.
Yeah, but that's a different x.
It is. The x in square, and that's kind of the point I've been trying to make. The x in square is a different x than the x in sum of squares.
Right, yeah.
And so that x takes on the value 6 first when we call square x, but then it takes on the value 7. It does not when you call it with square y, and you go times xx, even though in sum of squares, x is bound to 6. When you're actually evaluating this body of square, and you're calling square y, and y was bound to 7, while you're evaluating this body, x will be bound to 7.
Yeah.
Right.
Within that those specific parens that defines square y.
Exactly. Within the entire body of square. But note that the entire body of square is that one form, which is times xx, right?
Mm-hmm.
So it's just important to recognize this, that, that within a procedure, this is just a local binding. This is not a binding that escapes out into the world.
Yeah,
right?
yeah.
And if you type in x at the REPL right now, what do you think would happen if you typed in x at the REPL?
It would just, it wouldn't do anything, right? Because it'd have to, it's not bound to.
It's not bound at the REPL, at the level of the REPL. That's right. So you would get an error if you just typed in x right here, because x isn't bound to anything, right? Well, right, but that's different. But if you just put in x. But here's the thing. You could define x to be 42.
Yep.
But if you called square 6, you would still get back 36, because within the body of square, right?
Yep.
Now, what is interesting about that is that, and this I actually think is, maybe we should talk about this a little bit. So why don't you write a procedure here that takes no arguments but multiplies pig by pig?
Right. Oh, whoops.
Well, you want to define a procedure. So you know two ways of defining procedures. Well, hang on. You want to define a procedure. You don't just want to multiply pig by pig. You want to define a procedure that does that.
Oh, okay.
And you can name the procedure like square pig or something, right? Okay, if you're using define to define a procedure, though, it's got special syntax. That's right. So you can do that, or you can use a minus sign, and you usually do in Scheme. Use a minus sign, right? And this takes no arguments, so you can just close these parens right now. This is a procedure of no arguments, right? And now just open up some parens and do times pig pig. This is the body. Times pig pig. Multiply pig by pig. Close the parens and then close it all up again. And now try calling square pig. It takes no arguments. So you're just gonna, you're gonna apply the procedure to no arguments, right? Well, you still need the open parens to apply it. Right.
Oh.
So note something. These are what we call, these are free variables within it. A procedure can see its outer environment as well. So if something is defined in the environment where the procedure is defined, it can actually see those values if you don't shadow them. Okay?
Mm-hmm.
So in this case, it's actually reaching out into the enclosing environment and getting a value, and it is multiplying 42 by 42.
Yep.
This can get a little bit confusing, though. Let's say, okay, define a function called square 3 that takes one argument and name that argument pig. Close. And now multiply pig by pig. And so now try calling that and applying it to an argument, right? Because note that it does take an argument. So you can apply it to 6.
Wait. Okay, yeah.
Yep.
Yeah.
Okay, so do you see what's going on here?
Okay, so within square 3 now is bound to, right, pig could be anything within what's in terms of what it means in relationship to the function of square 3 function. No.
So when we define square 3, we say square 3 does take an argument, and within the body that you evaluate, right, we want you to bind the name pig to that argument. And so this hides, right? If you define a function that takes no arguments, or that doesn't take an argument named pig, right? We could have had square pig take an x and a y and a z, for instance. If you say times pig pig, first it looks at its own argument list, essentially. It looks at its own environment. And it says, I don't have a pig here. So I don't know what pig is, but I'm going to go look at the enclosing environment. And in the enclosing environment, there is a pig because we defined it at the top level. And so it multiplies pig by pig. It says, okay, that's 42 times 42, right?
Mm-hmm.
But when we define square 3, we did include the symbol pig in the argument list. So now when we evaluate the body of square 3, it's going to say that it's local pig, the pig in the local environment, which is, what the argument list, that's what it's going to use. It's not going to keep looking out into the other environment. So in this case, it's going to be the argument. Does that make sense?
Yeah, I think so. Yeah, it does make sense. It's a little bit, I I don't know. There's something that's surprising about this one where it's. Pig. I mean, I guess it already knows what pig is, and then down here, pig is a new thing. Is it back to that reference versus what was it called?
No, this isn't the use mention distinction, because in
Use
neither
mention.
case are we talking about the symbol pig. We're always talking about pig being bound to some value. But when we talk about symbols being bound to values, they're sort of bound to values within environments, right? And so one environment is the function itself. It has its own environment. And so
Yeah.
everything that's in the argument list, for instance, gets every symbol in the, when you apply it to it, it binds within that environment, the function's own environment.
Mm-hmm.
It binds the
Okay.
names in the argument list to those values. But it is also true that the procedure can see the environment that it was defined within, right? And this actually happens at the time that it gets defined, kind of. So it can see, and that is something that we will talk about, because we're going to talk about closures eventually, and this is very important to understand in terms of how closures work. But we're not going to talk about closures quite yet. But this is an important property, and it is important to understand what's going on. And what we can say is when you define square 3, and you say that pig is in its argument list, you are shadowing the value of pig from the enclosing environment, right?
The broader 42. Yeah.
Right. You can no longer actually get at that anymore,
Uh-huh.
right? Like that value of pig is hidden from you, and that's why we call it shadowing. It's hidden from you by this more specific value of pig, right? That's actually within this. So there's a set of rules for what environment things get looked up in, and the function's own environment takes precedence over the enclosing environment.
I mean, what if I do that? Doesn't that? Yeah. Okay. I got it.
Exactly.
Yep.
Yes. So, this can get a little bit hard to keep track of sometimes. It's important to understand this. When we talk about closures, it will become quite important.
Mm-hmm. Okay.
So I wanted to talk about how we've actually been seeing an exception to the rules we've talked about. We've seen a few of them, actually. So we talked about there being this rule that when you see an open paren, the very next thing after that open paren is something, it tries to evaluates that thing, which should evaluate to a procedure, and then it tries to evaluate that procedure to the rest of the things in the parens as arguments.
Mm-hmm.
And if it evaluates that thing and it doesn't evaluate to a procedure, then it's an error, right?
Yeah.
Except we've already seen some exceptions to this, haven't we? Look at the form of the lambda and note that its argument list is an open paren, x, and a closed paren. But
Yeah.
wait, x isn't bound to a procedure. So this
Not
is,
yet.
well,
I
x
see.
never is going to be bound to a procedure. We're going to bind it to a number when we call it with a number. But do you see that? Like in that lambda, that actually violates the rules that we've been talking about, right?
Yeah.
Okay.
Well, it's because it's in the middle of doing a lambda thing.
That's actually exactly what it is, which is that lambda is special. Lambda is what we call a special form. And
Right.
special forms have their own syntax within the special form. They can basically break the rules. And that's part of what makes them special forms. Is
Yep.
that they have their own syntax. There are some other things that make them special forms. And it is actually possible in Scheme to define your own special forms, your own things that do violate these rules in various ways. It is not possible to do it with any of the techniques that we've really seen so far, though. And I think it might be quite a while before we actually look at the ways that you do that. But note that you do have the power. One of the nice things about most Lisps is that they tend to put you very close to the level of the language implementer in terms of the amount of power that you have. Right? They tend to be very flexible languages that give you a lot of power to do things. For instance, there's a lot of stuff that's special in a language like C too, but you can't add more special stuff of your own, right? You're kind of bound by what the rules are. Whereas in Scheme and in other Lisps, there are a variety of mechanisms for doing that. But we probably won't look at those mechanisms very soon. But it is just something to be aware of. Special forms have their own rules. And we're about to kind of look at a special form that has its own rules and that is a pretty important one. So we'll look at a couple of them, actually. But One thing, so we've talked about different types of values so far, right? And some of the values that we've talked about. And the concept of type is a very important concept, actually. Things have types, right?
Okay.
So 42 has a type, and that type is it's a number. It's actually an integer, right?
Mm-hmm.
So that's a type that things can have.
Okay.
When you type in quote pig, right? Try that out. So if you're going to apply quote to pig, it's going to have to be in parens. Quote is also a special form, by the way. Right. Quote stops evaluation. That's how you know quote is a special form. We have no way of stopping evaluation yet. Other than using quote, for instance, but we can't ourselves just say, oh, don't evaluate this, right? Other
Yeah.
than by using quote. And that is one of the things that tells you quote is a special form, is that it controls the evaluation of its arguments. So pig is a symbol, right? We've talked about that. And what you were using passing to print line when we passed it returning 6, those things in double quotes, the type of that thing is a string. So if you just type in double quote high and double quote, just as an example. Okay, not that high. But yeah, that's a string, right? So that also has a type. And types matter. Try passing high to square, for instance.
Passing I to square.
Yeah, apply square to the string high. Right. It does not like this. Why?
It's like, aren't you going to give me a number here? Like, what am I supposed to do?
Right.
And you gave me high.
Right, because you're trying to multiply high by something, and it says,
I love how
I don't know how to multiply strings together, right? You can even
Yeah.
see that it's the star. You see that star colon, right?
Yeah.
That star is the multiplication, is the procedure for multiplication.
Yeah. Well, hey, we contracted that you're going to do this multiplication. Number? Hello. It's
Right.
kind of, I like how it has the question mark. It's funny.
Yeah, well, and that's actually used because there is actually a function, a procedure called number. So, and it has the question mark on the end. So try applying number to the string high.
Wait. Oh, gotcha.
This will segue very nicely into what I want to talk about next. It does have the question mark on it though.
Oh,
That's actually part of the name of the procedure.
gotcha.
So this is actually where I was going with this notion of types, is that I want to introduce a new type of thing. And that type of thing is Boolean. And there are only 2 values within this type. And that's one of them. Sharp F, which is false.
Okay.
So try applying number to 42.
Ah, yeah.
It is indeed. So this is true and false, and we call them Booleans.
Boolean.
Booleans, Boolean. And they're named after a guy named George Boole, who was a mathematician.
Okay.
And who developed a lot of mathematics around a lot of mathematics around the arithmetic of Booleans. So Booleans are extremely important in programming because we want to make choices a lot of the time in programming. We want to say, well, if this is the case, then do this, otherwise do that, right? But what is that if? It's like, well, if such and such is true, then do this, right? So whether or not things are true is important. And that number there with the question mark, that is something we call a predicate, right? It's a procedure that returns true or false. It is a predicate. It looks at its argument, it makes a judgment about it, in this case, whether or not it's a number, and it either returns you true or false. And it's a predicate. So if is also a special form for reasons that we will see in a minute. And let's see here. And like, most special forms, it has sort of its own syntax. And if basically has 4 parts to it. So let's try a very simple if. So if you type in open parens if, right? Because this is something that does get applied to things.
Mm-hmm.
And then hit space and do sharp T, right? And then space 6, space 7, close parens. Just as an example here. Okay, now try doing that same thing, but replace the true with a false, right? Which is sharp F. Okay.
Huh.
So the form of if is first the if to tell you that it's an if. That's the first
Yeah.
thing. The second thing is some expression. And if that expression evaluates to true, the third thing is the form that you evaluate and return if the second thing evaluated to true. And then the next thing is what you evaluate and return if the second thing evaluated to false. So you see what saying? So if this
Yeah.
first thing evaluates to true, return 6. Otherwise, return 7.
Does that mean given true false is basically a dialectic or whatever? It's a two option thing
Yep.
that you're going to have two arguments in there. You have to have two arguments, or
No, you have one expression and it will evaluate to true or it will evaluate to false. And it's a little more complicated than that, but I just want to treat it that way just for the moment.
okay,
The other two are your options: what to do if it evaluated to true and what to do if it evaluated to false.
okay,
Okay, so in this case, we say if this evaluates to true, return 6, otherwise return 7, right?
mm-hmm.
If the thing that we're evaluating is true, well, that evaluates to true. But you could, for instance, replace that, and this may make this a little bit clearer, do an if, but replace that second clause with number high, for instance, right? Apply number to high. No, apply number to high as this expression. So backspace over the sharp.
What are you saying?
So do you see how up above we applied number to high?
Yeah.
Do that again. Well, how do you apply something? There you go. You're right, the string high. Well, you still need the 6 and the 7, though, right? If always has, and this is not quite true, but if has 4 parts, basically. Okay. So if we were to say this in English, what we're saying is, if high is a number, return 6, otherwise
Yeah.
return 7, right?
So then, but it's not referencing the lines above in terms of true or false. I mean, what? I guess I'm.
Okay. So I'm not quite sure what you're asking, but let's talk about it, and I will probably figure it out.
So I think maybe the true and the false, the number sign true and the number sign false. No, those are symbols that the computer knows, right? Or maybe that's the wrong word.
Yeah, sharp T is our way of writing true. It's how we
Yeah.
write true. And note that true evaluates to itself, right? If you type in
Yeah.
sharp T at the REPL and hit return. Just like numbers, these things evaluate to themselves.
Mm-hmm.
That's the rule for evaluating them. So they represent the concept of true and of false. They're sort of a little bit conceptual in that sense, right? True is it represents the concept of something being true. And so if I ask you a question, right, is high a number?
Okay,
Well,
I got it.
If I do it in English, you're probably going to say yes, right? But if I do it in Scheme, I'm saying what is the truth value of this proposition? Does that make sense to you? I'm giving you a proposition. High is a number, okay? And I'm asking you to evaluate the truth value of that, the truthfulness of that. I'm saying, is what I just asked you true or is it false?
And if it's true, give me a 6, and if it's false, give me a 7.
Right. Well, the first thing that we're doing, though, is just when we talk about just applying number to high, that's a predicate.
Yeah.
And so I'm saying, is this true or false? Is high a number? Right. And then we put in the if. So number high evaluates to true or false. It is a predicate. That's what it does. Right.
Gotcha.
In this case, it evaluated to false because high is not a number. Okay.
Mm-hmm.
So you can look up above at the patterns that we gave where we just wrote out the true and the false as these very simple things. Right. You normally wouldn't really do this because it's a foregone conclusion. Right. You already know what's going to happen here. Right. Because you're actually literally giving it sharp T.
Yeah.
But when you give it a slightly more complicated thing like number high, well, number high evaluates to false. So it's going to behave the same as that second one. And that's the rule for if. If evaluates, so it's got forms 1, 2, 3, and 4, right? And we can ignore the first one. That's just the simple if, right? That's the first part of it. The second is an expression that evaluates to true or false, like number high, for instance, right?
Mm-hmm.
The third thing is what to do if the third form is what to evaluate in return if the second form evaluated to true.
Yep.
And the fourth form is what to evaluate and then return the value that you got from evaluating it if the second form evaluated to false.
Yep.
Okay. So if you type in if number 42 and then 6 and 7, what would you expect to get back?
6.
You'd get the 6 back. But yeah, go ahead and give it a try.
Yeah. And what about them? But the 6 and the 7 can be anything. I mean, they could be letters.
Right.
I mean, that could be like if I was for me, like this.
Well, that's going to run into trouble. Because remember, I said it evaluates those things and returns their value. But what's the rule for evaluating a symbol? You just typed in a raw symbol. Right? Try just typing T at the REPL right now. Right. So it's going to evaluate the third form and try to return its value. Right? What's the rule for evaluating just a raw symbol, though?
It refers to itself. I mean, evaluates.
No, that's not the rule for symbols. So what happens if you type in pi, pi?
It has to have a value. Whoops. Symbol. It has to be bound. The symbol has to be bound to a value.
So try typing in what you typed there, but instead of T and F, put in pig and pi.
With the 42?
Yep, try it with number 42. And before you hit return, what do you think that this is going to do?
Give me pig, I think. Oh.
Right, it's going to evaluate pig and return whatever pig evaluated to.
Now I'm confused.
Well, what happens if you type pig at the REPL right now?
Yeah.
Right?
Oh, okay. So it's not about the true or the false. It's right. It gave me 6 above because basically the thing it's evaluating is saying like, give me the first of these. Give me the third form, you called it, right? If it's true, and give me the fourth if it's false.
Right. And it will attempt to evaluate those forms and put them in simplest terms before it like sends it back. Right? So when you put in the T and the F, T and F are just symbols. T and F aren't bound to anything. Don't confuse them with sharp T and sharp F, right? Sharp T is how we write true. Sharp F is how we write false. Those two things have an evaluation rule, which is they evaluate to themselves, just like numbers do, just like strings do. But T and F are just symbols, right? So the rule for evaluating them is, you look in the current environment and you see if they're bound to anything, to a value, and you return that value. And then you look in any enclosing environments that are available to you as well, right? Which is what we were looking at earlier, that like if it doesn't find it in the innermost environment that it's in, there may be some enclosing environments. And so it will start looking at them. And we didn't really get into this, but you can sometimes wind up fairly deeply nested within environments, right? They nest like Kachinka dolls. So you could be 6 environments deep and you could be looking for whatever's bound to a symbol up through them. It might be that you would have to look through 4 of them to get to where it was bound, but that would be fine. It would look until it found something and then it would stop looking, right? And that's why they shadow other things, right? The innermost environment wins. If you have a symbol bound, if a bunch of environments have a symbol bound to a value, right? And you're within all of them, you're going to get the innermost, you're going to get the value from the innermost environment that does have that symbol bound.
Yeah.
Okay.
Yeah. Okay.
So you're seeing what's going on here with if.
Yeah.
Okay. So I've been lying a little bit to you about this, which is that, in fact, that second form does not have to evaluate to true or false. So for instance, you could type in if 42, 6, 7. Why don't you try that out?
You're saying 42 as the...
Yeah, but just it doesn't go in parens, right? Because we're not trying to apply 42. That would blow up, in fact, because it would be trying to apply 42, 6, 7. Yeah. Okay. So what's happening here is that when you evaluate something in a Boolean context, it will essentially get turned into, it will be considered to be truthy or falsy. And this is something that's true in a lot of languages, right? That you can put things other than true or false into positions that sort of require true or false. And it will decide, well, do I consider this truthy or falsy? It turns out that in Scheme, essentially everything other than false is just considered to be true. That's not true in all languages. For instance, in C, a 0 is considered to be false. But any non-zero number is considered to be true. So the rules change from language to language. We won't worry about that so much. Just recognize that in Scheme, pretty much any value other than false in an if will cause the first branch to be returned.
Okay.
And we haven't talked about lists yet, although I think that is about what we're about to talk about. So the if is very, very important. There is another special form called cond that also...
So just to understand that in this thing is saying if 42, it's almost like if a type, if the type we're dealing with is a number, 42 is a number, an integer, then evaluate that to these to the next thing, and if it's the same type, then return, then...
No, in the if, what I was saying is that almost anything in the second position of an if that isn't a false will be considered to be a true. It will treat it as if it were true.
But how does it even know, what would be a false? I mean, it's...
False would be a false. So try doing if, number high, pig pie, for instance. Try doing that.
Wait, number?
Well, apply it to high, to the string high, right? Just like you did to 42 above, but apply it to high instead. The string high, not the symbol, right?
We already did that one, then.
I don't think we did this exact one, right? So we get pi, right?
Yeah.
And the reason we do is that when we apply number to high, what do we get back?
False.
False, right? What I'm saying is that almost anything other than false, if that second form evaluates to basically anything other than false, it's going to treat that value as true.
But I mean, what's it? Okay, so it's just evaluating 42. It's
evaluating 42 to 42 because 42 evaluates to itself. It's kind of looking at 42 and saying, is 42 false? No, it's not false. So I'm going to consider it to be true.
Okay.
That's just kind of how Scheme works. And that's what I was talking about. Most languages have a concept of truthiness and falsiness. They're the actual values true and false. But in a Boolean context, where something expects to get a Boolean, it can often accept values other than true and false in that context, but it will treat those values as either true or false. And different languages have different rules for this, which is what I was saying. For instance, in the language C, a 0 is considered to be false if you encounter it in a Boolean context. But any positive integer, for instance, any integer at all, actually, other than 0, will be considered to be true. And so different languages have really different semantics around truthiness and falsiness, and it's something that you have to be kind of careful about when you are switching programming languages. You have to bear that in mind. We're not going to worry a whole bunch about it, except to say that basically Scheme considers everything that isn't false to be true.
Okay.
42 is definitely considered to be true in Scheme, as we just showed. So with the string high, right? So there are reasons that this is convenient. We'll see them. That'll become clearer over time.
And the string high would be considered true? Like I could just
it would also be considered to be true. Yep.
It'll give me 6. Okay.
Yep.
All right. Cool.
Yeah, pretty much anything that isn't false is considered to be true in Scheme. But false is definitely considered to be false, right?
Yep.
Anything that evaluates to it. And so number is not the only predicate. There's a predicate string, right? Try calling string with a question mark on the end. That is a convention in Scheme, is that a lot of things that return true or false will end in a question mark.
And then just do big.
Right.
It should give me 7. Okay.
Right. Now let's be very careful about what just happened there.
Whoops, I forgot my parentheses.
No, that was perfect. You did it exactly right. It did pretty much what you expected. What did it ask? So it asked if something was a string. What thing did it ask if it was a string?
Pig. Well,
No, not pig.
42, I guess.
42. And so this is what I'm getting at, I guess, with the use mention thing. But note that when you pass something to a procedure, an argument, the procedure never sees the symbol pig, right? Pig gets evaluated, and whatever it evaluates to is what gets passed to the function. And note, as I said, that's not something that has to be true in a programming language.
Okay.
It is true in Scheme, though, and it is in almost all commonly used programming languages. There are some programming languages that have various forms of what's called laziness, and there are different rules for evaluation, but pretty much all mainstream conventional languages work this way. So,
I could see that they would want to turn it into whatever, because I mean, you made a symbol out of it to kind of shortcut or simplify on some level, and the computer needs to actually.
Yeah, it's just a question of where you do the evaluation, and there are some trade-offs in terms of the two things. There are some advantages to both systems. In an awful lot of cases, you can't really tell the difference, right? But in some cases, you can. But we're kind of getting into territory that I think is a little bit deeper than I want to get into right now. But I just do want to point that out, is that when you apply a procedure to arguments, the arguments get evaluated and then passed to it. Now, here's an important point about special forms. That's not necessarily true of special forms. Special forms can control evaluation. But procedures can't. Procedures, all the evaluation has been done before the procedure sees things. It's arguments, right? If they were a thing that could be simplified, that could be evaluated and simplified, that simplification happens before the procedure is actually invoked. And all the procedure ever sees is what things got simplified to.
Okay.
Does that make sense?
Yeah.
Okay. And yeah, we'll talk about that even in reference to if pretty soon, because one of the things about if is that, I'll just mention it here, if only evaluates one of the forms. So when you say if high 6, 7, the 6 is never evaluated.
6 is never.
The 6 is, well, right. If you say if high 6, 7. Oh, I'm sorry.
Number.
Right. The 7 is number. The 7 is never evaluated in that
Right.
case. Right.
In the most recent one here, yeah.
And that's actually a really important.
It doesn't need to get there. It already knows.
It doesn't, but let's note that this is actually an exercise in SICP, which is they ask, can you write if as a procedure? And it kind of looks like you ought to be able to write if as a procedure, right? It turns out that you can't write if as a procedure, and this is exactly the reason that you can't, is because if does something that a procedure can't do, which is that it controls the evaluation of its arguments. It only evaluates one of them. Whereas if you call a procedure, all the arguments will be evaluated before they get past the procedure.
Okay. Yep.
And that turns out to be kind of important because those things could have side effects. So for instance, if you type in, try this. Okay, so open paren if space sharp false or sharp t. Yeah, try giving it true. And then the first form should be print line, well, apply it to arguments. So you have to open a paren, right? Print line, and then the string whew, like WHEW. Right? And now the fourth branch should be open paren print line and the string launching missiles.
It sounds like it has a background.
So these are side effects, right?
Oh yeah, print line.
Yeah. And now if you hit return, no missiles launched, right? Here's the thing. If were a procedure rather than a special form, both of those print lines would have been evaluated before if even got invoked. Do you see what I'm saying?
Yeah.
So it's quite important that if you don't want those missiles launched, right, if has to be a special form because you're making a decision about what to do.
But in place of number symbol T, I could have put 42.
You could have anything that it would treat as truthy, right?
Yeah.
But try doing that line above, but give it false.
Yeah, it would be, or I could do the number high
or
thing.
anything that evaluates to false, right? Yeah. So number high.
It should print the second one. I don't really want to hit send though.
It's okay. We're just simulating the missile launch here.
I don't know, man.
You never know. You never know, but this one's probably pretty safe. So yeah, so that's really, really important actually, right? And here's the thing. If these were sort of pure functions, like many of the ones that we've talked about, that just sort of calculate and return values, but don't cause a change in the world, right? Don't cause side effects, then it wouldn't be quite as dangerous for it to evaluate both branches because they don't actually cause anything to happen. But it could be expensive. These could be expensive calculations, right? It could be that the second branch is like some very expensive calculation. You'd kind of prefer that it not run if it doesn't have to, right?
Mm-hmm.
But if it were a procedure, it would have to because procedures cannot control the evaluation of their arguments. Their arguments are always evaluated and essentially brought into simplest form before the procedure even sees them.
Mm-hmm. Okay.
So this is kind of important, and we'll see some other things that are kind of like this here. If you have true and false, one of the things that you'd probably like to have is the concept of and, right? An and actually has some rules. There is an and. So try doing and true, true. Apply and to true twice.
That's it?
That's it. Try that out. Okay. So try do and true, false. Okay. What about and false true? And there's one more permutation. You can probably figure this one out.
That's a lot of falses.
It is. And can actually be applied to more than two arguments. That's not true in all languages, but it is true in Scheme. But if you're talking about two arguments, which is the most typical thing that you would use and for, and returns true if both of those arguments are true, and it returns false otherwise. So try doing and true, true, true. Okay. So basically the deal with and is that if all of its arguments are true or truthy, so you could also try and 4236. And note this. This will be kind of interesting. Okay.
Gives you the.
It gives you the last. It basically evaluates them and gives you the last one back.
Right.
Try doing and 42 false. Sharp F.
Right. It should be false. Yeah.
Yeah. Try doing and false 42.
I think that would also be false.
Right. So that's how and works, right? It evaluates all of its arguments. If it hits any of them that are false, it returns false.
Mm-hmm.
Otherwise, when it gets to the last one, it says, okay, this one was true or truthy, and it returns that argument. Yeah, right. You saw how that worked in the and 4236. And there's some debate over whether it is good style to use ands for their return value, other than treating it as truthy or falsy. There are some patterns you can use that kind of do that. So
Wait. Using it for its return value.
Using it for its return value, we'll get to that eventually.
Okay, so yeah, because it's returning the 36 and.
Right. Like using that 36 in a calculation, for instance, instead of just checking to see if it's truthy, right?
Yep.
So one thing about and, though, is that it short circuits. So try doing and 42 print line hi there, right?
Is that right? No, I got one.
Yeah, and then close them up. Okay. But try doing and false print line hi there.
It's false.
Right. Okay. So you can see that nothing got printed. So what we can say is that it short-circuited. As soon as it hits the false, it stops evaluating anything else. They don't get evaluated.
Oh, right. As soon as it's false while it's going down the thing, so it doesn't have to. Yeah. So it kind of operates like a procedure until it doesn't, because
So it doesn't. It's actually special because it does control. It does control the evaluation of its arguments. And just to be really clear about what we're talking about here, try squaring print line hi there. Try just applying square to print line hi there. I mean, we know it's not going to work. We know we're going to get an error because print line hi there actually doesn't evaluate. It evaluates to the absence of a value, essentially, which is not quite the same thing as, it's the absence of a value. So you'll note something. It blew up, right? Because it got into the function. It was like, oh my God, like, what are you asking me to like square here?
Mm-hmm.
And you can see what it gave you, which is void, that sharp void thing, which essentially means the absence of a value, right? I mean, the absence of a value is itself kind of a value in Scheme, which is a little bit funny, but it's represented by that sharp void. But if you go back down, you can see that it did print before it blew up, right? Because it evaluated the print line before it even invoked the procedure square.
Because it was doing because I had to,
Because procedures don't control the evaluation of their arguments. The arguments get evaluated before the procedure is invoked. And there's no way for a procedure to keep its arguments from being evaluated. Only special forms can do that. So it's a really important point, actually.
Yeah. Okay.
And so you can use, you can use this characteristic of and in a number of ways. One of
And
the
you just
Mhm.
sorry to so just
Sure.
in terms of special forms, you just know. I mean, that's something of since it's like a basic property of the language is something you learn as
Yeah, you kind of know what special forms and what's not. In a lot of cases, you don't have to care very much if they're special forms, right? In a lot of cases, there's things where I'm like, I don't, is that a special form or is that, but like, it doesn't really matter very much to me, right?
yeah.
But in some cases, it is. And knowing whether things evaluate their arguments and what the rules are for evaluating them is important, right? It's important to understand that and does not necessarily evaluate all of its arguments. If it hits a false somewhere there, it's not going to keep
Yep.
evaluating anything past there.
Yep.
There's also an or, right?
How does that work?
Well, what do you expect? So note that what we did, if we're talking about just the two arguments, when I had you type in the true true, the true false, the false true, and the false false, that's
Yeah.
actually something sort of called a truth table. When we talk about these operators that operate just on two arguments, we can actually draw up, but there's only four permutations, right?
Yep.
Of true and false. So we can actually say the truth table of this is is what it returns given for each of those permutations. So we know for and it returns true for true and true, and then for all three of the others it returns false. What would you expect or to do?
Starting to get late. like, uh, I, I don't know. I guess I'm having a hard time conceiving
Okay,
of it
no
uh,
problem.
without
So
if.
and is basically saying are all of these true?
Mhm.
Or is asking if any of them are true.
Oh, so it's gonna it'll be the flip side. It'll be keep evaluating until you hit it true. And if you don't, then return.
No, actually, you pretty much have to evaluate. Well, right, until you hit a true. As no, that's exactly right. I'm sorry, I'm being dumb. You're exactly correct. Keep evaluating till you hit a true, and at that point, hey, that's fine. So try doing or 4236 though, or even or false actually. Try or false. I'm sorry, or 42 false, right?
It should be 42. Yeah.
Right. And it will give you back the value of that first true thing. And it never even got to there. And the same thing would have happened if you do or 4236, right?
Oh, this does the first one.
Exactly. Because it knows at that point that it can stop evaluating now. As
Yeah.
soon as it hits a truthy thing, it can stop evaluating. Whereas for and, as soon as it hits a falsy thing, it can stop evaluating.
Yeah, sure.
Right?
Okay. So, yeah, it was true. Yep.
So, one thing to note here about this is that English uses or in two different ways. And this is one of the ways that we use or. But for instance, if you're in a restaurant and your server asks you, would you like soup or salad? And you say yes, it's not going to go over well. In this kind of or,
You should know though.
an acceptable option would be sure, I want soup and salad. But well, no, it's soup or salad, but not both.
Yeah.
But note that this or is fine with both. So there's another one, and I'm pretty sure. Just make sure that I remember this correctly in scheme. Yes, it's actually XOR. So try XOR 4236. But XOR 42 false. Right. So XOR means one or the other is true, but not both.
Okay.
And the X stands for exclusive or. And so soup or salad is sort of an exclusive or, right? You can have soup or you can have salad, but you can't have both. And I guess in this analogy it's a little strange because you also can't have neither. They're going to make you eat one of them. Right? But
They're at least going to bring it to the table. But yeah, no, it's kind of yeah.
so these are the most important operations on Booleans, and you can use these to build up more complex Booleans, right? So Here's an example. Less than is something that you can ask, and it's just I mean, it's the symbol from mathematics class, right?
Yeah, which is going to be
That left angle bracket.
this guy.
It's like over your comma. Yeah, exactly. So you can ask less than 3, 6. Is 3 less than 6?
So it reads the first.
Yes.
That's true.
And if you flip those two numbers,
False.
okay. So you can also ask,
I can do more than also.
why don't you ask if 42 is both a number and less than 50? Well, that's a greater than. Oh yeah, you're okay. Yep. You're playing
Okay.
greater than. Exactly. Exactly.
So what we were going to do, we're going to ask if
Ask if 42 is both a number and less than 50.
okay. Um, um, yep. If like,
Okay.
uh,
You actually don't need an if here, right? You can write this in terms of an and.
oh, because I'm asking it two different. Yeah. If is it whoops. Oh yeah, no, no. What are we doing? 50?
Well, 42, actually. We're asking if 42 is a number and if it's
Yeah,
less than 50.
I gotta do another one of these tonight.
Yep, that looks good. Ooh, that's a little funny. So this isn't quite right. Because you wanted to ask if 42 was less than 50. You just asked less than 50. The 42 doesn't carry over into the next set of parens, right?
Uh, yeah, I wouldn't have any way of knowing over there.
Right.
So I gotta put in 42 twice? No, or can
Yeah,
I put
you do
42
have
on
to
the
put
other?
in, yeah, you need to put in 42 twice,
I
basically.
can't do I can't do 42 here,
No,
and because
it's, you
that's
really do have to just kind of ask number 42 and less than 4250, right? Now, there are some ways you could bind it to a temporary name if you know, but that wouldn't save you a lot of typing in
unless I
this
was doing
case.
a bunch of times. Yeah,
In fact, it would add a lot of typing. You could use a let to do this. You could also write,
I gotta do
yeah.
this.
Sorry, I'll stop distracting you here. I'll let you do your thing. Yeah. Okay.
But, yeah.
So
So but on this one, this is just a true thing, even though it's not. It's back to that thing of like, well, it's not false, so it's true.
well, actually, no, this is the behavior of less. So try typing in less 50. Less has weird behavior if you only give it a single argument. And well, you do need the parens. You're applying it, right?
Whoops.
This is just how less works. Uh, and I don't really want to talk about why at this point. Don't worry about it. Like, you're never really going to do this. You're always going to apply less to at least, you're always going to apply less to at least two arguments. Right? You're going to
And
say, I'm sorry?
yeah, and I'll read the first one and evaluate it against the second one.
Yeah, exactly. It's going to say, is 42 less than 50? And in fact, less can be passed more than two arguments too. You can, and then it's sort of like, is each of them less than the next one, right?
Oh, so it's got to not just 42 against each one of them, but it has to be
Right.
ascending.
Yes, exactly.
Each
So less
okay.
than.
So and that's the and function again. Like
Well, that's just less. I mean, less itself can take three arguments. So try typing in like less 42, 50, 52. Or 54. That's fine. Okay. But now replace the 54 with a 46.
yeah. Okay. Yep.
right? Because 50 is not less than 46. So it just keeps going. You're basically asking, are these numbers like sort of in increasing order, right?
Yeah.
So let's note something. What happens if you ask if high is less, the string high is less than 50? So, right, this doesn't work. It's
Real.
a real, which is a real number. You're familiar with the concept of real numbers, right?
Yeah, pretty much. I mean, it's been a long time.
So we should actually talk about that a little bit more at some point, the types of numbers. Let's just talk about them very, very briefly, though, right? So, you have probably I always actually forget a little bit what the nomenclature is for this, but you have like the counting numbers, right? Which is like 1, 2, 3, 4, 5, 6, right?
One, two, yeah.
And then you have the positive integers, which is 0, 1, 2, 3, 5, 6, right? Or, yeah. And then you have, well, those are the non negative integers, actually, I guess I should say. Then you have all of the integers, which include negative numbers, right? So it's 0, 1, 2, 3, 4, 5, 6. It is also -1, -2, -3, and so on for quite a while.
Yep. How
And
long? Ago?
so you'll note that, again, this is sort of like nested Kachinka dolls. We keep making a slightly larger category that includes everything from the categories before it, right? So the next category that we tend to come to is the rational numbers. And these are numbers that can be expressed as the ratio of two integers.
Hmm.
So 1/3, for instance, right? 1/3 is a rational number because it's expressed as the ratio. It's the ratio of 1 to 3. It turns out that if you write something out in a decimal format, like 0 point whatever, so anything that terminates that has a fixed number of digits after the dot
Yeah.
is going to be a rational for sure.
Uh-huh.
Um,
Like half translated to 5.
right, 0.5. But you know that
Yep.
if it's got a fixed number of digits, it also happens to be true that if it has an infinite number of digits, but it repeats, right? If it's like 0.635, forever, that's also a rational number.
How do you know? I mean, some stuff you just know that it's not going to change, but
Well, you do have to know that, right?
I guess if it, no, it wouldn't necessarily. I'm just trying to, yeah, if it repeated once, then it just is going to keep repeating, but that's not
Not
necessarily
necessarily true. You could have 0.635, going off to infinity, and that would not. But don't worry about whether or not we know. Just like note that that is a number, right? 0.635 forever. That's a number, right? And
Yeah.
it turns out I don't know exactly what the ratio, what integers that's the ratio of, but I know from its form that that can be expressed as the ratio of two integers. But then you get numbers that don't repeat, that have an infinite number of digits after the decimal point, and those digits don't repeat, and those numbers are irrational, and they
Mhm.
cannot be expressed as the ratio of two numbers.
Mhm.
And a very, very long time ago, this was an open question. Are there numbers that can't be expressed as the ratio of two integers? And so a very early discovery, I guess, was that the square root of 2 is an example of an irrational number.
Hmm.
For reasons. It comes up a lot because it comes up a lot when, for instance, you're calculating like the diagonal of a square, for instance. And it comes up in various places, the square root of 2. And there's sort of a nice, elegant proof that it can't be
Yeah.
expressed.
No, I mean, that is interesting, but I'm probably not where we want to go right now.
Yeah,
Okay.
we don't want to look at that proof. But it is just sort of a little bit of the history of mathematics there. So the real numbers encompass all of those categories that we've been talking about.
Mm-hmm.
You may have heard of complex
Oh,
numbers.
real, even irrational numbers are real also.
Irrational numbers are also real. That's right.
Yeah.
The real numbers encompass all of those. There are numbers that are outside that system as well. And you probably haven't really seen them very much, but you've probably heard of imaginary numbers, right? At least heard of
Yeah.
them. Okay, so there is something called this thing. Real numbers all fall on the real number line, right? You probably remember the number line, right?
Not really.
Okay,
No, but
just like a
but
line with some markings on it, right? There's a marking for 0, there's a marking for 1, there's a marking for 2. And so the real numbers all fall somewhere on that line.
yeah, they're going to be in relation to it.
So
Yeah.
complex numbers have sort of another part to them that means that they actually define a plane. So some complex numbers actually do fall on the real number line, but many of them fall on other lines that are parallel to the real number line. And therefore they define a plane. And that's probably all we need to say about them at the moment.
Hmm.
And Scheme actually has a built-in, not Scheme, Racket has a built-in complex number type, but we won't deal or talk with that much. If though we wanted to do, for instance, something with fractals, like we wanted to write a program that, are you familiar with the Mandelbrot set? It's like the most famous fractal. I'm sure you've seen a lot of like psychedelically colored posters of it. You'd
Yeah.
recognize it if you saw it, for sure. So calculating the Mandelbrot set, for instance, involves working with complex numbers.
Hmm.
But we won't worry about that at the moment. But it is good to just have a feel for like, okay, there are these categories of numbers. So what this is saying is that less than expects a real number.
Yep.
But here's a kind of important point about this. So what happens if you try typing in and number high and less than high 50?
Where you're saying like,
Yeah. Just like we did with 42, but replace 42 with high. So now you're going to ask if high is less than 50 as well. That's the second bit of the and. Okay. What happens if you reverse those two tests? So you ask if it's less than 50 before you ask if it's a number. Right. So do you see what happened here? Why the first one worked and the second one didn't?
well, yeah, because the first one it looks at it and says, okay, that's false. I don't need to go any further.
That's right.
But
It's because it
yeah,
short circuits evaluation.
uh, okay,
Because you can't
yeah,
ask if high is less than 50.
yep,
But if you put the two things into the and, you don't get to the second one. This is actually a really common pattern in real programming. So you could have something you don't know if it's a number or not, and you kind of want to do this check, and this keeps things from blowing up. You typically don't want things to blow up in your programs.
hmm,
That's a larger topic, the topic of errors and handling errors and recovering from errors, right? But an awful lot of the time, you're just like, okay, so is this both a number and it's less than 50? And you can safely ask both of those things if you do this in the right order.
but will you do that off on the side somewhere or something? Yeah, I don't. What do you? Okay, I mean, I know that maybe is probably. We're not even really talking about that aspect of.
Well, so in
I,
this case, we already know that high is not a number because it's a string and we're typing it straight in.
yep.
But let's note that it actually could be something that got passed into a procedure, or it
Yeah.
could even be some input that was given to you by a user, by something from outside your program that you don't have control over, for instance, right?
Mm,
So you
okay.
might not know if it's a number. And you might want to be
Yep.
like, well, so this kind of thing is a very common pattern, using this short circuiting to avoid blowing things up, right?
Okay.
Because it's safe to ask this question: is this a number and less than 50, as long as you do it in the right order, so that
Yep.
it does
Yep.
short circuit. So that's just sort of something that follows on from the stuff we were talking about. And then there's one more operator on Booleans that I want to talk about, which is not. So try doing not true. Okay. And vice versa, right? Right. So that's the truth table of not.
Hmm.
And if you so if ask if like high is not a number.
Yep.
Yeah, it's not a number. Let me ask you something. If you were to type in number pig using the right parens, what would the answer to that be?
Uh, it should be true
Should be true. Why should it be true?
because pig, I'm not going to use the right terminology, but translates to, a pig is a
It is
bound,
bound.
yeah, it's
It is
bound to
bound
a
to the
value.
value of 42, right? But what about number quote pig?
That's a string because
That's a string.
that's not a number.
That's not a number. And what about quote pig?
Just
Just a
with,
single quote.
with a number thing.
Yeah, well, ask if number space quote pig. Do you remember quote? No, it's just the it. No, no, you were fine, just except for the last quote. It's not surrounded by
Oh,
quotes. It's just a quote in front of it.
well, that just is back to itself, so it also seems false, isn't it?
That's right. It evaluates to the symbol pig. This is this
Yeah.
use mention thing that we talked about a little bit. It's the symbol pig, and the symbol pig is definitely not a number. But if it's just number pig, it's going to evaluate pig first. And it's going to say, okay, yeah.
But it'll just be true, not the actual value. Yeah.
Right. Yes, because number is a true predicate. It actually returns true or false. So yeah, so Booleans are very important. Like we need to make decisions and do things.
Hmm.
So based on things, we have to ask questions and do things. And this is sort of where programming sort of begins. Everything we've been doing up until now is just typing in expressions that evaluate to a fixed thing, which is not necessarily all that useful. You kind of already know what they're going to evaluate to, right?
Yeah.
But now that we can actually make a decision and do different things based on a number of conditions, we can actually start to do some things that are a little bit more useful. So that's good. Now, the other thing is that.
Hold on just 1 second here. I gotta
Sure.
grab a
Sure.
stand up. Grab a drink of water, but it's right over here. This table has got like a flap that bounces, so hopefully it's not making a noise. Okay.
Okay. So something else. So up until now, we've been dealing with things that are simple values, that are individual values. And you could argue a little bit about the strings, right? Because the strings are actually made up of multiple characters, I guess, right? Like the string is actually the character PIG.
Yeah.
But it's pretty much still a single, I'm going to say atomic value, right? It's a simple value in that sense.
Mhm.
We often want to bundle things together in
Yeah.
various ways. We want, we don't want to deal with things individually. So, and I'm kind of thinking about what the right order to kind of approach things in is, whether to talk about pairs first or lists first. And I think we'll talk about lists first, even though in some ways the pair is the more fundamental concept. We'll talk about them both, I guess. We've actually seen a lot of lists already because Scheme has a property, Lisps in general have a property which is known as homoiconicity. And we won't talk too much about that right now. It has fairly deep implications. But what that means is that Scheme programs are actually written in Scheme data structures. And that's not true of most programming languages. Most programs in those programming languages are not data structures within that language, except in the very, very trivial sense that they are strings. And most of those programming languages have strings, have a text representation. But there's no internal structure there. Scheme, though, is actually made up of lists. And you can look at these programs like number ? Pig in parens is actually a list in Scheme. So if you type in open paren list space 123 close parens.
Like so, or
Yep, just like so. You just apply list to those arguments. you actually get back a list. And note that there's a quote in front of that list.
Yeah.
Okay? Well, try typing in quote open paren 1, 2, 3, 4. This gets you a list. What would happen if you left the quote off?
Be an error, wouldn't it? It's not a. It wants to treat it like a procedure.
Right. It wants to treat one like a procedure.
Yeah.
Right. So the rule for evaluating lists in Scheme, when we talked about that rule for evaluating like open parens, that's kind of the rule for evaluating lists if you rate them in literal syntax, right? If you rate them in, if you have this literal syntax of a list, it does it. So you do need the quote. But we can type list and we can get a list. And there is a little bit of a subtle distinction here, which I don't think matters in Racket, but certainly in Common Lisp, it's very important that if you're ever going to change a list, that you make a new list by using the list keyword or some other things that make new lists rather than using the quote form. Because the quote form actually allows the implementation. And this is something I don't really want to talk about, to be honest with you, but I feel like I have to mention it because it's kind of important that in some Lisps, it's not safe to use the literal syntax if you plan on actually modifying the list. So I'll just get that out of the way and we won't worry about it too much from here on in. But it is a pretty common source of errors in Common Lisp programs with beginners is failing to do that.
Okay.
So try typing in quote open parens, close parens. Okay. This is the empty list. This is kind of an important value, actually, for a variety of reasons, which we'll see. Try typing in just list in parens with no arguments. Okay. So, again, we see that we get the empty list.
Yeah.
You can put lists inside of lists, right?
Yeah.
So try doing that. Try making a list that consists of the number 1, then a list with the numbers 2 and 3, and then the number 4.
No, I did that with one.
So you don't, yeah, there you go. This isn't going to do quite what you think it is, but keep going because this will be sort of educational. Okay. That's probably not quite what you expected.
No.
The quote stops evaluation in the quoted form. It stops all evaluation in the quoted form. So this list, you apply it to arguments, and when you evaluate its application to those arguments, it gives you back a list, right?
Yeah, which includes...
But you used a quote here. So the list never got applied to its arguments because that's a form of evaluation. So in fact, you can type in what you were typing there, but just leave the list out, right? And this is important to understand. That quote just stops all evaluation all the way down. Yep, there you go. So there's another way of doing this, though. Try doing it without using a quote. How would you make that list without using a quote? Right. So here we didn't use a quote. So we are following normal evaluation rules.
Yeah.
And it tried to evaluate open paren 2, 3, and it's like 2's not a procedure.
But this is going to be a new list, isn't it?
Yes, it is. But it's a list nonetheless, and lists can contain other lists.
Okay, so it doesn't, right.
I mean, these two values are essentially what you got back from using the quoted form and what you got back by using the list to build the lists. They're very equivalent, other than, as I mentioned, in some Lisps, there is a difference between making quoted lists because of something called interning. And I really don't want to talk about that, but I feel like I just have to mention it a little bit because it's something you have to have in the back of your mind in some Lisps, right? Like it
Hmm.
kind of gives me the heebie-jeebies a little bit. Not really, but I'm aware when I see that quote in the list, and this is from writing Common Lisp a fair bit, of like knowing that I can't modify this list. And that if I want a list I can modify, I have to like create it in a different way that gets me a completely new list. So I think in Racket, and do not quote me on this, but I think you get a new list using the quote as well. I'd have to look into it though, because I have not done a great deal of Racket programming. Racket is pretty new to me, and the truth is, it's been a long time since I've done much scheme programming either. So, yeah, so I'm a little bit unsure. But I think it's safe to modify these. I still wouldn't. It would bother me. So, this is not the only way to make lists, and we should actually talk a little bit about what lists are. So there's something called cons, and cons stands for construct.
Hmm.
So if you cons the number one onto the empty list, why don't you try doing that? Like apply cons to the number one and to the empty list. So it's C-O-N-S. It has an S on the end.
Oh, right.
Yep.
Yeah. Um,
To the empty list, which does need a quote. So cons one and then the empty list. Okay. Try consing 1 to 2.
what's cons? You said is construct?
It stands for construct, but cons is this thing that makes pairs, actually. And so this bit is this is going to take a little bit of discussion, but I just kind of want to show you some things. You see that there's a dot in there.
Oh, yeah.
This is a dotted pair. This is not a list. This is not a proper list.
Okay.
So that's what I'm kind of thinking about how to actually get at this. Proper lists end with the empty list. So when you cons a 1 to a 2, you get what's called a dotted pair.
Hmm.
When you cons 1 to the empty list, you get a pair basically of 1 in the empty list, but the fact that the empty list is what sort of ends it is what makes it a true list. I'm not explaining this very well. I should probably have thought a little bit harder about how to explain this before this, actually. Because what I don't want to talk about too much is what's happening under the hood in the computer.
Yeah.
But we probably should talk about eventually con cells and how they work. But I don't really want to get into that right now. I want to treat lists as these abstract things. They have the rules that they have, partially because of the underlying implementation. They're a form of linked data structure. But try consing 1 onto the result of consing 2 onto the empty list.
So consing 2 onto an empty list would be.
Yeah, don't quote it. Just cons 2 onto the empty list. So open parens, cons.
Oh, another cons.
Yeah. Right. So that needs like a space and a quote. Right.
What the?
Cons 2 onto the empty list, right? It's just like when you cons 1 onto the empty list. It's the same
Oh,
form
right.
for this internal thing, right?
That?
Yep. And we get the list 1 too. So if you have a list and you
Oh.
cons something onto that list, you get a new list that is a list that contains the thing you consed onto it and then everything else that was in the old list. Do you see?
Let me just look at this for a second here. The first one is kind of confusing me a little bit. Why did they put you got 1 in an empty list?
And that
So-
gives you back a list with a 1 in it.
Yeah, because the empty didn't have anything in it, so all you're left was your 1 that you had to start with. Right.
Yeah, and cons can't make lists without starting from a list. I guess that's one way. of thinking about it, right?
Okay.
The sort of last thing in your cons chain. To make a list, you have to cons something onto a list.
Uh-huh.
Cons makes dotted pairs if you just cons 1 and 2 together. And you can cons different things together. You could cons 1 to high there, and you'd get a dotted pair that contained 1 and high there. But dotted pairs are not true lists.
Okay.
And it's just kind of important to recognize that. They have their uses. There are times when a dotted pair is exactly what you want. But we use lists a lot more. And so it's just sort of important to understand this rule and maybe like sort of withhold judgment a little bit at this point. That's not quite the right word. Suspend disbelief, like hold it in abeyance. If that seems a little bit weird, just don't worry about it too much. It's just a rule. It just works this way, right? And
Yeah.
we can look later on, we can look a little bit more at why it does. So you see where you did cons 1, cons 2 to the empty list? So can you use that same pattern using cons to make a list containing 1, 2, and 3?
Um, and couldn't do that.
This one's a little tricky. So see here, I'm going to show you, and then we can take a look at it, and maybe you'll start to see the pattern.
Yeah. Okay.
So open parens and do cons 1. Space. Open parens again, do cons 2. Space. Open parens again, and do cons 3. Then the empty list.
Oh,
Well,
it's
don't
gonna.
close your parens. Cons always takes 2 arguments, right? And now just close up all your parens.
Okay.
So the rule with cons is that if you cons something onto a list, you get a new list with what you consed onto the list and then everything else in the list. So when you
Okay.
cons 3 onto the empty list, you get a list with 3 in it. When you cons 2 onto the result of that, which is a list with 3 in it,
Yep.
you get a list with 3 in it, right? When you
Yep.
cons 1 onto that list, you get a new list with 1, 2, 3. Does that make sense?
I think so, but you always has to have that empty list thing in it. That seems a little bit weird.
Yes. Remember what I was saying before about how the fact that the last thing in here is the empty list, that's what makes a list, is consing a value onto the empty list. You
Okay.
need to
So,
start with a list to get a list, basically, right?
and the empty list is what you're starting with, just as like the structure, essentially, or
Right, because
something.
we want to start off, we're building up this list out of these repeated operations. So
Okay.
the very
Yep.
first thing we want is we want a list with 3 in it, right? To
Yeah.
get a
This is
list with 3 in it, we have to start with some list, but it has to be an empty list because we don't want anything other than the 3 in it, right?
yeah.
You
Gotcha.
cons the 3 into it, into this empty list, you get a list that's 3. And then you're like, okay, but I want, now you can get exactly this same list by doing list 1, 2, 3 without a whole bunch of intervening parens, right? Try that out again. We've seen this, but let's like reinforce this. Yeah, okay. So this is the same, and you might wonder, well, why would I want this cons thing? And the truth
Yeah.
is that if you just wanted to get this by writing something down in literal syntax, you would never do this thing with cons. You would write list. The thing is, you often want to build up a list in steps, and
Yeah.
this allows you to do this, right?
Hmm.
Now let's note something. We're not changing any lists here. We're making every cons is returning a brand new list.
Hmm.
So nothing's getting changed. Try consing 4 onto that list that you just put in, right? So cons 4. Ooh, getting somebody spamming porn links in the chat.
But with using cons, just to see, but it's going to put the at the beginning.
It will. You're not going to get them in order now. Yes, you will get 4. Actually, but not the result of these cons is. Just do the list that you did above, list 1, 2, 3. Cons 4 onto list 1, 2, 3. You will need 1 open parens, but yeah. Right. So that gets you that. And we don't, when you do list 1, 2, 3, you do get the empty list at the very end of it, right?
Mm-hmm.
So the cons actually shows you something about the internal structure, like how the computer is actually doing this, right?
Yeah.
The list is kind of a shorthand in a way for this process of construction.
Yep.
And one of the reasons that we do this is we may want to build up a list in steps. We may want to repeatedly be adding something to the list, and we're going to see some patterns where we're going to do exactly that. We don't know what everything is all at once. We want to start off with an empty list, and then we want to add one thing to it, and then we want to add another thing to it, and then we want to add another thing to it. And so cons allows you to do that.
Mm-hmm.
Now, you may also want to get at things in the list. And so why don't you define list 1 to be the list 1, 2, 3, 4.
Define list 1, you said?
Yeah, just bind that name. Just so that we don't have to keep typing this out,
Yeah.
And if you put in list 1, you'll get back what you expect to get back, right? This evaluates to that. So one of the things we can do with lists is we can ask for the first thing in the list. And just for sort of historical completeness, I will show you the historical way of doing this, which is car, C-A-R. So try doing car list 1. Apply car to list 1. Okay. And then try doing cdr, which is CDR. Try applying that to list 1. Okay, you may be wondering what is car and what is cdr, and this is actually this has to do with a very old computer architecture where they had some things called registers as part of the hardware, and there was something called the contents address register and the contents decrement register. And you know what? You never have to worry about that again. It's completely irrelevant. It's just a historical detail. However, in early Lisps, this is how you got the first thing in a list and the rest of things in a list, and you will still see car and cdr used in literature in some places. However, and I'm pretty sure, let me see if I can get this right in Racket. So try first list 1.
Doing for first list, what?
So you can actually spell it out. It's just FIRST. List 1.
Okay. Can you do third?
Well, very specifically, try doing rest. You can do third, actually. Try doing rest list 1.
Throws out the first.
It throws out the first. And it turns out this is a hugely important pattern. You don't really need third, for instance. You can build third out of first and rest. So using just first and rest, how would you get the third thing in list 1?
I would do. Well,
how would you get?
I got to go back to the.
You don't need an or. You can do this entirely with firsts and rests.
I'm trying to do. Well, I got to do first twice.
Let's get the second thing first of all, right? Let's get the second thing instead of the third thing because it's just a little less typing and a little easier to conceptualize. How would you get the second thing in the list using just first and rest?
Without making a new list?
Without making a new list, you can just refer to list 1. Let's think about this. What's the rest of list 1?
2, 3. It's everything except for the first item.
Okay. What's the first thing in that?
1.
No.
The first thing in the rest
The first thing in the rest
is 2.
is 2. What were you looking for when you were, if you were going to do second?
Yeah.
That would get you the 2, right?
Yeah.
So what happens if you do first of the rest of list 1?
I mean, literally of.
No, no. Just apply first to the result of applying rest to list 1.
Oh, I see. But I can then do it.
So open, yep.
But
Yep. Now, what if you wanted to get the third thing in the list?
um, but
It's not quite that.
I missed the parenthesis. Oh
Nope,
no.
it's not about that. So let's think about what you're doing. So you work from the inside out when you're applying procedures like this, right? Because the very first thing to happen is you get rest of list 1, right? And then
Yeah.
you get the first of rest of list 1. What's the first of rest of list 1?
2.
I'm sorry, what?
It'd be 2.
It would be 2. Then you're trying to apply first to that. What's the first of 2?
2.
No. The first of 2 is an error. And you can
Well,
see that's what this error is telling you. It's a contract violation. And what it's saying is that it wanted a list and it wanted that list to not be empty.
mhm.
That's what this error message actually means. You can actually see that it's using a predicate. It's using an and here. So it's saying what I'm expecting is that what you give me is it is a list and it is not empty. That's how you read
Yeah.
this particular error message. We'll talk about
Make
contracts eventually. So
3.
you can't take the first of 2. If you
Do
try
the
typing
rest.
in first 2, you'll get exactly that same error message. Exactly, because that's in fact what caused that error message. Is you tried to take the first of 2. First works on lists, and it works on lists that aren't empty. So you were pretty close, but think it through Think it through a little bit more. We want to get the third item in the list. So what do you
Yeah.
have to do that?
Um, Need the rest of it after you take. Uh,
So apply rest to it once, right?
yeah. You get 3,
Yeah.
2, 3, 4.
Okay, we're looking for the 3.
This would be.
Yep, that's right. Now, I will just point out again a weird little historical thing. I'm not sure I should really encourage you to use these because it's sometimes considered bad style by some people. One of the things about car and coulter is that you can actually put them together. So you could also open parens and say CDDR and then list 1.
Hmm.
Okay, now try doing CADDR. So it's sort of a shorthand that basically says, get me the car of the coulter of list 1. And that's the same thing because car equals first and coulter equals rest. It's the same thing
Mm-hmm.
as saying, get me the first thing of the rest of list 1, right? It's equivalent. I'll just point that out. It's a little, and this is used in some literature. So it's good to know this. And there's actually like a set of rules. If you're kind of, if you've been doing Lisp for a while, there's ways of actually, that is pronounced the cateter.
Okay.
And these could be built up. I think that at least in Common Lisp, it's guaranteed, I think, as part of the spec. I think you have to be able to use at least 10 of those letters for it to be a compliant Common Lisp thing. So you could write the cadadadatter, for instance. That's a thing. I would say that it may be kind of bad form to use things with, like, say, 10 of those letters all struck together. It can be a little bit hard to read.
I would imagine. Although the caterer definitely makes sense if it's more. Nah, anyway,
Yeah.
I am starting to try to make some joke about, you know, when stuff is wackier and more cat-like than others.
Really, I was going to go straight for Caddyshack. But
That's probably more appropriate given the spelling. But,
yeah. So there is a reason. There are some reasons to really want to think about these things in this way, and you can see that this is sort of symmetric in some way with the cons, right? We sort of construct lists out of heads and tails, right? When we use a cons,
mhm.
the first thing in the cons becomes the first of the resulting list. And the second thing in the cons becomes the rest of the resulting list. Do you see that? So it's a
Yeah.
symmetric operation in some sense. So cons puts things together. First and rest take things apart. You can almost think of them as deconstructing the list. Cons constructs lists. First and rest deconstruct them. And if we sort of split a list into first and rest, we get a symmetrical operation, right? With the first corresponds to the first argument of a cons, and rest corresponds to the second argument of the cons. Do you see that?
Uh,
So try consing 1 onto the list 2, 3, 4. Right. And we get back what list 1 is, basically, right?
yeah.
So try taking the first of list 1.
Yeah.
Now try taking the rest of list 1. So note something. These are the two arguments that you would pass to cons to make the list 1, right?
Hmm. Yeah.
If you basically cons the head of the list onto the tail of the list, or the first onto the rest. And I think, let me just see something here. Okay. So in some languages, and it's not synonymous, this does not exist in Racket or in Scheme, I guess. Head and tail are also sometimes used as first and rest. And I may sometimes use that nomenclature because I think about lists this way in a lot of cases. It's the head and the tail, right?
Okay. Yeah.
So when we talk about making lists and we talk about that empty list that you add to cons onto at the end, what we're saying is that if you keep taking coulders of a list, eventually we will get to the empty list. If we keep taking rests of lists, right?
Yep.
If you take the rest of a list, now what happens if you try getting the rest of the empty list?
I would think that would be an error.
Give it a try.
You mean just any old?
Rest, yep, just of the empty list. And this does give you an error. That's not actually true. I have seen some implementations where this actually just gives you back the empty list too. But in general, right, in Scheme tends to be pretty precise about this. And it's like, don't ask me for the rest of something if it has no rest. The empty list has no rest. Any other list does. And so you see this contract here. Rest expects to get a list, and it expects that to not be the empty list.
Mm-hmm.
Okay. So that's
The C is the contract in that.
yeah. The C is there because this is in contract. This is because it's part of the contract system. So these particular things are used, and we'll talk about the contract system a little bit. You can write contracts for your functions, for your procedures. So when you write your procedure, you can put a contract at the beginning of it and say, could you please check that these things are true of my arguments?
Mm-hmm.
And then if they aren't, it will give you a nice error message like this. You can write a procedure, like for instance, our procedure square. that checks to see if it is a number. And that's actually what happens in Square. If you pass it something that's not a number, you run afoul of the contract for multiplication, because that does have a contract.
Got it.
You
Yeah.
could write your own contract for Square, though, that did that same check. And
Yeah.
indeed, it's pretty good practice to do that for code that matters, because things will still blow up, but at least it will give you a good explanation of why it blew up. And sometimes that's very valuable, right?
Mm-hmm.
Catching an error right at the very first place that you can. The very first you want things to blow up as early as possible. That's just a general rule. If they're going to blow up at all, you
Yeah.
want them to blow up as fast as possible.
Yeah.
So this symmetry of cons and first rest turns out to be very, very important. And what we will be talking about next time, we're not going to get into it tonight because it is difficult. But what we'll be talking about next time is going to rely, some of the things we'll be writing there will rely very heavily on this.
Cool.
I would like to just sort of show you, I mean, I know it is getting late, and if you wanted to stop a little early tonight, that would be fine. I mean, I think we talked about normally going from 8 to 11, but I don't think we have to be rigid about that if you're tired. But if you feel like keeping on going for a little bit, we could keep on going and just look at a few things.
Here's a little bit more. I get, you know, I get a little bit less. Yeah, it's just, I'll retain a little bit less, but I can,
Sure.
It's not like I'm falling asleep in my soup.
You're eating soup. I want soup. I'm jealous now. I actually had basically a lentil chicken bacon carrot stew tonight. It was good.
It's good.
I like soups and stews. They're among my favorite
Yeah.
foods.
That's fine.
So we've talked about lists a little bit, and we briefly saw dotted pairs. I think I want to take a little detour here, and I'm kind of thinking because, well, all right. So you did see, for instance, I guess we'll look a little bit more at lists at least. So you did see that there are names defined for second, third, fourth, fifth, etc. Right?
Mm-hmm. In the list.
For lists,
Wait.
there are functions defined that get the second element, the third element, the fourth element, the fifth element.
By using cons or, yeah.
Well, no, but there are actually names. You can also just like there's first, there's also second, and there's third.
Oh, yeah, when we were doing that. Yeah.
Right. So we
Right.
can get those things. We can get the third element just using firsts and rests. And it's important to understand that you can do that, that you can deconstruct lists in that way. But there are also built into Scheme. You could build your own out of first and rest if you wanted to. If that didn't come with Scheme, you could build your own. You see that, right?
Yeah.
Using first and rest.
And
One-
defining. Right? You use define to.
Yeah,
You-
you could define a procedure. You could define second, and the body of second would just be, you'd have something like LST might be the name of the argument. You don't want to use LIST as the name of the argument, because list is already a procedure that you don't want to overwrite, right?
Yeah.
List already exists as something, but you could use LST as the name of your argument. And then you could just say, for second, it would just be first of the rest of LST. And for third, it would be first of the rest of the rest of LST. And for fourth, it would be first of the rest of the rest of the rest of LST.
Yeah.
And so note, one of the things that you can actually see if you look a little bit closely at this is that first attempt you made it at second, that was first rest, it has to be wrong. Because we know that this list contains values, list one contains values that are not themselves lists. So as soon as you call first on it, you know that you're going to get something back that isn't a list. So you're not going to be able to call first on it again. Do you see what I'm saying?
Mm-hmm. Mm-hmm.
Now, because lists can actually contain other lists, first rest of a list is not always an error, right? If the second thing in your list were a list, that would get you something, but it would get you something out of the contained list, right? Do you see that?
Yeah, it would be the first thing in the contained list. Yeah.
Exactly. So if the second thing in your list were a list,
Yeah.
then you would get the first thing in that list.
Yeah, instead of the digit 2, there was another parentheses with whatever.
3, 4, 5, 6. Right?
Yeah, it would return 3.
It would return 3. That's exactly right. So lists are really, there are other data structures, but I'll note that you can, like, sort of early versions of Scheme didn't really have a lot of other data structures built in. Racket does. Racket has a whole bunch of types of data structures, which we'll talk about some later on. But it turns out that it is possible to do most of what you want to do. You can pretty much do anything you want to do just using lists. It's just not always convenient and not always efficient. But they are sufficient to do a great deal with. Among other things, you can represent trees with lists. And when you have a list inside a list, you have a tree.
Okay.
And I don't know if that's super clear to you at this point, but we'll take a look at that at some point. There is one. I'm sorry.
No, I mean it just sounds like a definition of the thing. I mean, I can definitely picture lists inside a list. You could see that could go on to a great number of lists. There'd be a lot of branches on the tree.
Right. It's a way of representing trees, and that's something we'll probably talk about at some point because trees are very, very important.
Yeah, I mean, I don't know what trees means, but it's
okay.
like.
Well, you know what a family tree is, right?
Sure.
Okay.
Yeah, I mean, I can picture, I can imagine what it is. I just don't have any experience with it in this context.
Sure. And we'll talk about them eventually because trees, it turns out that tree-like structures that have branches, right? Because a list is just sort of a sequence of items. But we might want to have different sort of branches, right? You can think of, say, a list that contains two lists as being something that branches. The first list is one branch of the tree and the second list is one branch of the tree. And if that first list contains some lists itself, you'd get another level of the tree, right? It would branch to those things. And you could have that kind of a structure. And trees become very important. So one thing I also want to talk about, though, is functions as arguments to functions. And something we'll do pretty soon is we'll actually write a version of map, which I'm about to show you. But try typing in this, open paren, map, square, and then list one.
Cool.
So you see what that did, right?
Yeah, it squared all the separate values in the list in list one.
Right. It applied square to list one. And map can also take two lists as long as you give it a function that can take two arguments. So try mapping sum of squares to list one. Well, you're not applying it. You're just giving it as an argument, the procedure itself, not the result of applying it. And then maybe make a new list using literal syntax, because you want to actually give it two lists now.
A new list?
So you want to give this an extra argument. So make a new list after list one. Make a new list. You can type it out using the quote, for instance, like quote open parens.
Yeah.
2, 3, 4, 5. So what happened here is that it took the first element from list one and the first element from list two, and it called sum of squares with that, and that became the first result, the first value in the result, right? So that was a 1 and a 2, and the result of calling sum of squares on 1 and 2 is 5, right?
1 plus 4.
Yep. And then...
What?
I'm sorry?
I'm a little bit lost here. How does it know to add those together? It's applying sum of, okay, so it I got it. Map sum sum of squares to two. These are the two different lists, list one, and then the list that I just created using that quote.
Right. In list one, you have to imagine that list one is there, I guess. It's a list containing 1, 2, 3, 4.
Yeah, yeah.
So if you pair the first values of list one and list two together, you get a 1 and a 2. If you pair the second values of them together, it's a 2 and a 3, right?
Okay.
And then the third value of them paired together is going to be a 3 and a 4.
Yep. Yep. 2 and 3 is going to be 4 plus that 13. Yeah.
So map can take more than one list. It can actually take as many lists as the number of arguments that the function you pass to it is. But what just happened here is something that's actually quite important, which is note that we passed a procedure to another procedure as an argument.
Yeah.
That's not something you can do in all programming languages. For instance, in C, which I've referenced a few times, you can't do that directly. There are ways of sort of getting that effect in C, but they're kind of roundabout, right? But like the thing is that procedures do not exist at runtime in C in the same way that they do. They're not first class, is what we call it. First class are things that exist at runtime.
At runtime, you're saying?
At runtime, when the program is actually running.
Okay.
But in Scheme, procedures are absolutely first class. When you have a procedure, you literally have that procedure around, and you can pass it as an argument like anything else. You can even have procedures that make new procedures, by the way. And let me see if
So the map procedure.
So let's think about it just in terms of the bit where you pass it one list, because that's simpler, right?
Yeah.
So what's going on is map takes a procedure and a list, and
Does
I'm
Go
sorry.
ahead. No, go ahead. I'm not.
And
Yeah,
so
takes a procedure. Yeah.
what it returns is the result is a new list that is the result of applying that procedure to each element of the list that was passed in as an argument, right? And you get them back in the same order, right?
So map this procedure against this list, kind of like, yeah.
Yeah, we usually talk about mapping things over lists.
Okay.
We map it over. And so it's called map because it maps one value to another value, right?
Mm-hmm.
It's sort of like a map in that sense. When you have a map and you point to a point on the map, that maps to some actual location in the real world, right?
All right.
There's sort of a one-to-one correspondence of points on your map and points in the real world.
Yep. Yep.
Given that there are an infinite number of points, assuming that there's an infinite number of points, there's sort of the same number of points on the map, right? So for any point on the map, there's an exact corresponding point in the real world that corresponds to it. And for any number, right, functions actually map values to values, true mathematical functions. Procedures don't necessarily, because procedures are not necessarily true mathematical functions. But true mathematical functions just map values to values. And square is a true mathematical function, right? It takes a number, it gives you another number. If you pass it the same number, you always get back the same number, right? So it maps numbers onto other numbers. So that's kind of cool that we could do that. Let me show you another predicate, which is even ? So try giving that some number. Open parens, even ? And some number. And indeed, that is. And there is also an odd.
Oh, I thought even 42 is a number?
Even 42 is a number, yeah.
I mean, come on, 42, that can't possibly be a number. False.
Okay. So these are some predicates that exist for the numbers. For the integers, right? It doesn't make a lot of sense to ask if like a rational number that isn't a non-integer number is even or odd. But so try typing in open paren filter even list one. And you can do the same thing, filter odd list one.
And it has to have the question mark?
Yeah, that's part of the name of the predicates.
Right.
It's just the name of the procedure. You
Okay.
could certainly write procedures even and odd that didn't have the question mark, but this is a convention in Scheme that predicates tend to have question marks at the end of them. I will say that the majority of programming languages do not allow you to put question marks into names. Scheme is a little bit unusual in that, and so there are some conventions in Scheme. It's also very common to see things, and we will see some of these eventually, that have exclamation points at the end. And that's actually kind of a warning. It means you are about to change something. But do you see what filter does here?
Yep.
Okay.
Yeah.
So filter is also very useful, but note that it is, again, a higher order function. It's a higher order procedure in that it is a procedure that takes a procedure as an argument. And we'll actually see some ways like how you would go about writing filter and how you would go about writing map. And there's a number of ways you could do it. They happen to come built in, so you don't need to, but it's good to know how to build these things yourself, right? Wondering, another thing, let's see, is, let me just check something out here. I'm pretty sure that in Racket, but I always need to check a little because I use a lot of programming languages. So we were talking about lists before. This is just a good function to know about with lists is length. So you can try length of list one, and it'll tell you that. It's just sort of, I'm kind of like sort of covering just a few little dribs and drabs. Since I know you're tired, I don't want to do anything too incredibly hard here.
Yeah. Cool. Yeah, could I do, how would I do? That do it?
That'll do it. Yep. Because you're handing it a list. And let me just make sure that this is what I think it is. It is not. Okay. So here is actually a very interesting one because we've talked about procedures that can take procedures. Let's talk about a procedure that returns a procedure. There's one called compose. Do you remember this from, like, you probably looked at this in school a little bit, the composition of functions?
I would not remember.
Okay, so try typing in compose, not, and even. It's got to have the question mark.
Oh, the even, right?
Okay. So that returns a procedure. The result of applying compose to two arguments is a new procedure. It is, by the way, synonymous with odd. I'll just mention that.
Yeah, right.
If you compose not and even, so what it is that it calls even, it applies even to an argument. When you compose things, they have to take the same number of arguments. That's sort of a rule about compose. Even takes a single argument, not takes a single argument. Well, that's actually not true. That's actually not true. I'm sorry. When you compose things, and you can compose more than one, but let's just talk about two. I don't know. I'm getting tired too, because that was totally wrong what I just said. Is that not has to take as many arguments as it has to take arguments that match what even returns, right? So it's going to take one argument, but it has to be the right kind of argument. Not, by the way, takes Booleans, even returns a Boolean, so it works, it fits. But what we're doing when we compose these arguments, these functions, these procedures, is we say, first apply even to its argument, and then take the result of that and apply not to that result. and return that value. Does that make sense?
Yeah, I think so. Yeah.
Okay.
Yeah.
So we get a new procedure back that does that. So try filtering list one with that compose. Try using that as what you pass to filter as its first argument. Yeah, it's a paren issue. You need to close the compose. You need to close the compose after the even. And the not there is misspelled.
So it's a new procedure, filtering that procedure too. Okay. Yeah.
Right. Because as we said, not even applies to this. So another thing that I believe you ought to be able to do. Just thinking about whether or not there's another good example of compose using only stuff that we have available to us. Here's one you could do. Try composing square with itself.
Be a big number.
Well, not that big. I mean, just raising something to the fourth power.
So need an apprentice back there.
Well, yeah, sure. If you want to apply it to something, you're going to need to do that to see it work.
No, I don't need to. This should be. Yeah. Okay.
Right. So, and maybe we'll call it after this thing. But can you think about? Let's think about how you would actually go about writing your own compose. Try writing a version of compose. Like call it my compose.
Who we talking about? Defining it?
Yeah.
Like to be able to use it again? Okay.
Okay. Remember the rule for define, though. You actually have to start it with some parens, right? If you're defining a procedure, if you're using define to define a procedure and you don't want to use lambda, you start it with some parens.
Oh.
Right? And now you give the name of the procedure.
Oh, that's only for okay. Yeah, I was looking for the name of the work. Okay, and then
how many arguments does it take? Compose.
Two.
But hang on. Well, we're not going to use compose in this. We're going to write our own compose. But you're still in your argument list, right? So you're defining a function that takes 2 arguments. And I would probably name them something like func1 and func2. F-U-N-C. Func1, right? And func2, right? Because remember, we're setting out, let's remember how define works when you're defining a procedure, right? You have this argument list here that starts with the name that you want to bind the procedure to and then has a list of the names that will correspond to the arguments that you apply the function to. And this is a function that gets applied to 2 arguments, right?
Mm-hmm.
Okay.
Mm-hmm.
So we want func1 and func2, and that's what somebody's going to pass us. Like that would correspond to like the not and the even in the first thing. But it's whatever people pass to you, right?
Yeah.
And now you want to close the argument list, right? Now you want to write the body of this. And so
what do I want to? I mean, do if I'm going like the square thing, because I'm a little bit. Um,
So we need to return a procedure here. We don't have to name the procedure, but we need to actually return a procedure. How do we make procedures?
um,
And let's stipulate, by the way, that this compose, that func2 should be a procedure that takes a single argument. We should actually stipulate that, because there's some language features to make it deal with things that take a variable number of arguments. There's some language features we'd need to know that we don't know yet. So let's just say we're writing something that composes that func2 has to be a function, that both these functions have to be functions that take a single argument and return a single value.
so for procedure, we need to.
So how do we actually make procedures? Because we know we want to return a procedure, right? That's what compose returns. That's the type of thing it returns.
Do the thing and then have the body. Have the.
But what do we use? What do we use to define a procedure, to actually create one?
Oh, lambda.
Lambda, that's right. So we're returning a procedure here. I'm just going to this is not obvious. This is actually kind of a difficult thing, but I do want to show you how it works. So I'm not going to make you rack your brains too much, but this needs to take one argument, right? Because we're returning a procedure of one argument. We've kind of already established that.
Mm-hmm.
So how do you make a procedure of one argument using lambda? Well, no, you don't want to shadow the names. This is a new procedure. But
I mean, it would just
you
be
just
one.
need to give it some name, like an x. X would be fine, for instance.
Okay.
And now I'll pretty much just point this out to you, because this is kind of difficult given where we're at now. So, but I'd like you to see how it works. You don't need to apply it. You're just returning it.
Okay.
Okay. Lambda of x. And then what you want to do is apply func1 to the result of applying func2 to x. So how do you apply func1 to something?
Oops.
What's the rule for applying procedures? Yeah. And we want to apply func1 to the result of applying func2 to x.
I don't know how to.
My cat. Oh my gosh. I'm sure you can hear him, huh?
Definitely. He's time.
Yeah, he wants some attention. He's like, "Come on, buddy. What are you doing? You've been sitting there talking for almost 3 hours. You have not paid attention to me at all." He gets unhappy. Yeah. And now try closing up your procedures, your parens. Let's see what happens. Let's see if I got this basically right. This is actually if this is not entirely clear to you, that's really, really fine. We'll walk through it next time. This is a little bit complicated, but try doing my compose. Not and even, right? You get a procedure back, right?
Hmm.
So try applying that to 42.
My composed to 42.
Well, no, the result of actually calling my compose on not and even to 42, right?
Okay.
So you will need an extra, well, not quite. So you're going to need an extra paren at the beginning, right? And then you're going to need to close that paren after the even, right? Well, hang on. You don't need two question marks. You do need a closed paren there. Yeah, there you go.
This is the John. No.
Right. Which is sort of what we hope. This is what we want to see, right?
Not even false. It is even.
That's right. But when we compose not and even, what we get is something that's basically equivalent to odd,
Yeah.
right? So this is what we expect to get. This is like, okay, right. Is this not even? And yes, this is.
But I guess we may have to go over that whole thing because it couldn't I just
Oh, we
do
will. Yeah, we'll go over it again. Absolutely. This is I will say this. This is actually in some ways fairly advanced stuff. What we're looking at here. You can't quite do that. What you can do is wrap the even 42 in parens and do that. Right?
the wrap 42.
The even 42. Apply even to 42 and then apply not to the result of that. This you can do.
Mm-hmm.
But let's look at the
Right, because these are two different functions, not an even.
right. Well, mostly that not expects to get one argument.
Uh,
And what it does is it flips the logical sense of that argument. So not receives one thing, and if that thing is true, it returns false, and if that thing is false, it returns true. Right?
mm-hmm.
Not just flips the logical sense of this. I think, though, this is actually fairly difficult stuff in some ways, and it's also quite late. What I would do is, before we get off, I think you may want to copy some stuff into your upper buffer. Either that or just save this session here. One or the other. I don't think you want to get rid of all of this stuff, right?
Yeah.
We probably should have been working. I kind of thought about this earlier that I wanted to mention this, which is that working at the REPL like this can be like it's good for testing stuff out, but you really do want to be putting stuff into the top or somewhere to hang on to it. So you can.
Yeah, I know. There's certain things that I had actually it'd be helpful to take some notes, which I think I'll probably just have the laptop open and I can take them like in my and just have some running notes on stuff.
Sure. But actually
Yeah,
putting some of this stuff into the top would be pretty useful. It is possible to
yep.
just save a REPL session though. So maybe for right now that's what you want to do because I know you need to get off and I also need to get off because my cat is losing his mind. So why don't you save the REPL session? I don't think we really added anything to the top here. But if you go to the file menu, so which thing are you saving? What did you select? Because if you hit just save, I think you're saving the top.
That looks like it.
But if you go
Missed
to your
that.
file menu, it should have something there. Huh.
Save definition.
Try going to save other. What's in that little? Try doing save interactions. Yeah, try doing this and just say like session 3 REPL. Yeah. And don't, I mean, yeah, I guess you can save it to documents if you want. I would
Yeah.
probably save it. Where did we save stuff to last time?
I think I had it in documents, but I'll
Okay.
get a folder. I don't have. I mean, I have so few that at this
Yeah.
point, it's easy
We'll
to find
want to
stuff.
organize some stuff at some point, but this is fine.
But I'll take a look at it and to see if that saved it
Why don't
or.
you, yeah, can you try opening that up in a text editor of some sort? Do you have, like, even just pop it open in Visual Code or something? Yeah. What happens if you open it? Yeah, there you go.
Yep, that's
Yeah.
it.
And that's kind of what we wanted. Because definitely you may want to look back at this stuff to
Yeah.
refresh your memory a little during the week. And we're going to want to refer back to it to kind of recap next time. Because we covered a lot of stuff tonight. And
Yep. Yeah.
especially the stuff at the end, the stuff with my compose. I will say that this thing with higher order functions, even though it seems like a simple idea, this is difficult stuff. Like I watched people certainly when I was studying computer science, this was kind of we're looking at this kind of thing in a class that most people took the first semester of their sophomore year. So there's a lot of people who had been taking computer science for a year, and I watched a lot of people really struggle with some of these ideas in that class.
Mhm.
I mean, so be aware some of the stuff we're doing, and I kind of said this at the outset that I was kind of just going to kind of throw you into the deep end a little bit. A lot of it may not be immediately obvious. This is not actually easy stuff. I think that it's the kind of thing where it's not as hard as it seems once the penny drops on a lot of it. But
Mhm.
getting to that moment of the penny dropping, I think, it can be difficult. So don't feel like don't feel bad if it isn't immediately obvious to you. I'm kind of giving you somewhat intentionally, but I'm kind of feeding you some fairly difficult stuff. Especially for how much we've been going over. And we may actually back off a little bit and just sort of do some stuff that's.
No, I mean it's good to like kind of struggle because some of it's sometimes just terminology and getting, you know, just not that it's the repetitions of
Right.
function procedure, the proper, and just I mean that's just like muscle memory with some of those things. Getting into this kind of stuff, sure, I'm kind of like I don't know what I'm doing here, but with the
Yeah.
function, that was right at the end and stuff. But most of the rest of it, I'm like, oh, that's cool. You can do it. It does make pretty good sense, and then it's just a matter of the repetitions and actually like, okay, what is it that we're doing here, and how do I continually repeat it in the proper way and understand what it is I'm doing, you know?
Right.
Um,
And one of the things that we'll start doing pretty soon is we'll start actually writing some small programs that do things. And one of the
mhm.
things is things tend to get what happens is that you start doing that and you're like, oh, I want to do this. And you're like, oh, I don't quite know how. And then you figure out how to do it. You're like, right, right, right. I already know this. I need to define this procedure and stuff. And as you do that, as you say, it's repetitions. It kind of gets burned into you and you're like, all right. And it becomes routine. You just sort of automatically do it after a while.
Yeah,
But you do have to do that, right? You do have to actually do that. And actually like writing some code that does something is very helpful for that. We don't quite have the tools that we want yet
yeah.
to be able to do some of the stuff. One of the things though that I'll mention is that Racket comes with this sort of built-in system for doing simple graphics and actually graphics that can be interactive, where you can write these graphical programs that interact with the user. And it's a pretty neat little model for that. And I think we'll play some with that and just sort of write some programs that do things. And that'll give you a chance to really like, but I kind of want to introduce a variety of tools that we'll be able to use before we start doing that.
Yeah. Nice.
And so that'll, there is one thing that I do want to get to before we start doing that, which is pretty important in Scheme, especially if you were writing in Scheme that wasn't Racket. Because Racket has a whole bunch of stuff in it that especially was not in the early versions of Scheme. But even the modern version, Scheme is a very small language in terms of what has to be there for it to be considered a scheme. And then
Mm.
actual individual scheme implementations can add a whole bunch of stuff to that, but it's not part of the core language definition.
Mhm.
So Racket adds a whole bunch of stuff. There's a whole bunch of stuff in Racket that is not part of the Scheme spec, and especially there's different versions of Scheme, but and there's R4RS, R5RS. That's like version 4 of Scheme and version 5 of Scheme, and
Mhm.
especially if you look at like R4 RS, which is what, for instance, SICP was written to. It's a small language. So, so some of the stuff we're going to talk about, because there wouldn't be very much built into Scheme, this would be the only way of doing it. In Racket, that's not true. Racket, you have a lot of other tools, but I think it's still really good to get this concept of being able to take this very small core and build everything you need out of it. Now, you probably wouldn't really if you were writing like a program that you wanted to do something, right? A lot of the time you're going to take stuff other people have built. But I think it's really important to understand how that stuff is built. And one of the things that you do see a lot these days is people learn to program, and a lot of what they learn to do is sort of hook together libraries that other people have written. And you can get quite a lot done that way. But if they're libraries that you yourself have no idea how you would go about writing them, that can eventually be a problem. It's good to know, if you had to build tools for yourself, it's kind of good to know how to build as many of them as you can. And eventually you get to a point where you just couldn't. I mean, I couldn't, for instance, design my own chip for a computer, right? Like, I wouldn't even begin to know where to start with that. Eventually, you just sort of have to rely on stuff that other people have done. But I do,
I would see that even if you would know how to do it, it's like you don't necessarily want to, but I would think that maybe you do want to like be able to look at it if you need to and know what it is that you're looking at.
I guess so. Although if you're talking about an actual chip, like a CPU for a computer, yeah, you're not going to look at that, right? But if you're talking about a library somebody else wrote, then you might want to be able to look at that, absolutely. But also knowing these things, it helps you grow and mature as a programmer. But the other thing is sometimes you need something done that's on that level of complexity that nobody has written a library that does it. And you do have to write it yourself. And so if all you've really learned to do is to plug other people's libraries together, then you have a problem at that point. You've hit a wall where you have a thing you want to do and you can't do it because the library doesn't exist.
Yeah.
And then you do have to know how to write it. So so we're really building things up from very much from like kind of from the ground up here. I think, like, for instance, if you wanted to be a professional programmer in 6 months, I mean, first of all, we wouldn't be spending 3 hours a week on this, right? You'd be spending 40 hours a week on it. And we'd probably be just laser focused on practical stuff. And that's kind of, I don't know if you've heard of boot camps.
Yeah.
That's kind of what boot camps do. And I'm not going to, and I don't want to sound like I'm criticizing boot camps. Like, I think, it is a good way for people to come into the industry and get their first jobs. If, it has certainly worked for many people to do that. So you can't really criticize that, right? That's great. And then you learn more. But you do have to learn more, I think, because one of the things about boot camps is that they tend to skimp a little bit on fundamentals, right? There's a lot of fundamentals. And that's not really a criticism. You kind of have to do that if what you want to do is go from nothing to being able to actually write software in 6 months. There's some theoretical stuff you're just not going to cover in there. You have to pick and choose. But I think in the long run, at some point, if that's what people do, I think they need to go back and get some of those fundamentals.
Well, and sometimes if it's like other stuff, if you start learning and thinking about things in a certain way, it can make it more difficult to actually understand it, if you go back to it afterwards.
It's true. It is true. And it's also sort of a little bit painful in the sense that you sort of feel like, okay, well, I'm past the point of having to struggle with stuff, right? And then you have to go back and start rebuilding some of this stuff. And you're like, oh, I'm struggling with this. And like, I don't know, people don't like that. And there's a tendency to kind of want to turn that stuff off and say, well, I already know this stuff and I can get things done and I don't struggle. And so that feels good. And now I go back and I do this and I feel like I don't know what I'm doing and that feels bad. And since I already have the option to have it feel good by staying within what I know, I think I'm going to choose the feel good option and not choose the feel bad option, right? So it can be a little dangerous there. The other thing is the more you kind of understand about the principles of some of these things, so you can think about like stuff that is the eternal verities of programming, right? Stuff that's just always true and will always be true of programs. Yeah. And a lot of the stuff we're talking about is, Scheme is in some sense somewhat arbitrary, right? Like there could be other choices. So there's specifics to Scheme. But a lot of what we're really talking about is stuff that is sort of part of the eternal verities. Whereas learning how to make things appear in a web browser, it is true that web browsers have been around for a long time and they will be around for a long time, but like using a specific programming language to do this particular specific type of thing in a web browser, et cetera, et cetera. I mean, it's very useful. You need to know that if you want to do things that appear in a web browser. But if you understand the generalities, the stuff that's sort of always true, it actually turns out that it's easier to work from the general stuff to the specific stuff than vice versa, right?
Sure.
And it's much easier to pick up the specific stuff if you have a mental framework for why it works the way that it does, than if it's just sort of like, well, I have to memorize these things and I don't completely understand it. So I think that there is some real value to kind of starting really with the fundamental stuff of computing.
Yeah.
And that's kind of what we're doing. So
No, it's cool and it's fun. It's like it's a bit of a mystery too. Like it's very concrete, and then I'm like, huh. So yeah, this is making sense. How the hell do you take this stuff? You know?
turn it into computer programs. Yeah.
Yeah.
I mean, listen, that sense continues to stay with you just like on a different kind of scale, pretty much forever. I often wonder this exactly, like, how am I going to turn this stuff into a computer program? It's just, the stuff is a little bit more complicated.
Yeah.
But yeah, I mean, it is fun. I will say, there are sometimes some things about programming that can be extremely frustrating. And when you do it professionally, there's a lot of stuff. I mean, we're leading a whole bunch of stuff. We're not writing commercial software here, but when you write commercial software and you do it professionally, there's a lot of stuff that can be kind of tedious that just has to be done, right? It's sort of bookkeeping stuff and like keeping things clean stuff and code review stuff and version control stuff. We haven't talked about version control yet, but we probably should pretty soon. At least the basics of version control, which is really, really neat. I will say one thing and then I'll let you go, which is learning to use version control I think it's a really powerful skill to have, even if you're not a programmer, because there are a lot of things that you might want to put under version control. Version control allows you to, it is kind of what it is. It allows you to sort of keep track of a whole bunch of versions of things over time and like go back and forth between them and have a history of like when you changed them and how you changed them. And that's extremely valuable for a whole bunch of stuff, but it is something that has never quite really, other than very, very simple cases of it, like Microsoft Word has a little bit of version control built into it, sort of, right? Some facilities that are sort of like version control, but are nowhere near as powerful as like the version control systems that programmers use. And it's something I think a lot of people would benefit from understanding. It's just that it is a little bit tricky, and especially because most sophisticated version control systems were written for programmers. And they were written for people with a certain set of skills that most people don't really have. And so they're hard. They're kind of hard to use if you're not a programmer, but they're powerful tools. I think a lot of people would benefit from knowing how to use them. Anyway, I should let you go. It is late, and the cat has luckily stopped yowling, but probably not for long. So,
All right.
that was fun. I would definitely suggest that if you get a chance, take a look over this REPL session, see what makes sense about it, see what doesn't make sense about it. You can ask me about what doesn't make sense, but yeah, just kind of reinforce it in your head, because we actually did cover all kinds of stuff tonight. So
Yeah. No, it'll be good. Definitely.
okay, cool.
Cool,
All
man.
right. Well, thank you very much, and I will talk to you next week.
Definitely. Yeah.
Okay.
Thank you.
All
Talk to
right.
you soon.
Bye bye.
Bye.